Okay. Okay. So good evening, one and all. Before starting today's session, just let me recall what we have discussed in the last session. So yesterday we discussed about the basic concepts of DFT. Like there we understood like what exactly the quantum mechanics, what is the molecular mechanics, then what is the difference between the quantum mechanics and molecular mechanics, then when to use the quantum mechanics and when to use the molecular mechanics. So then we discussed about the what exactly the DFT, how exactly this DFT will work, then why should we need to perform the DFT calculation, and what are the different applications of DFT calculation. And we also discussed about the basis set and type of basis set, then functionals, then different types of functionals, then how to choose the functionals. So all those kind of things we have discussed. After that, we demonstrated you how to download and install the Gaussian software in your local machine. Then we demonstrated the basic usage of the software, like how to use the Gaussian software to, and we discussed like learned like different modules of the Gaussian software, the overall interface of the software, then how to draw the structure of your interest. Either it may be organic molecules or inorganic molecules or metal complex, or it may be like a solid materials. You have to follow the same procedure. So in today we are actually going to perform the DFT calculation. So whenever you are going to perform the DFT calculation, the first step is the geometry optimization. Okay. So whatever the calculation you'll do, first you need to optimize your structure, then you need to perform the calculation. So today we are going to learn how to perform the geometry optimization. Okay. Either it may be organic or inorganic molecules or metal complex or any 2D materials. You need to follow the same procedure. The first thing is how to prepare your structure. From that structure, you need to prepare the input file. So then you need to perform the calculation. Okay. Now, the question will come. So like why geometry optimization is needed? So what information will get by performing the geometry optimization? Because this geometry optimization using your DFT calculation, it will give like several information about your molecular system. Okay. So once you optimize your geometry, so it will give the most stable conformation. So where the forces on the each atoms are minimized, giving the bond length, the bond angle or dihedral angle of your system. And even you can get the information about the total energy, the overall energy of your system. Okay, the total electronic energy of the optimized structure, and which can be used to compare the stability of like different conformation. So like consider your structure is like exist in like 3 different conformation, and among those 3 conformation, you need to find out that which conformation is more stable. In that case, what you need to do is just perform the geometry optimization of all the 3 conformation and find out the total energy of the conformation and compare the energy. So which conformation of the lower energy, it will be the more stable, right? Because it is very basic information. So lower the energy, higher will be the stability. And you can also get the information about the molecular orbitals. Okay. So from there, like the energies and the shape of your molecular orbitals, we can calculate what is the homo-LUMO of your molecular system. And then I can get the information about the electron density distribution. Like it will give the information about the distribution of electron density within the molecule. So which can help us to understand the reactivity and properties of your molecule. And even you can calculate the polarizability, the dipole moment, the vector of the molecule by performing the geometry optimization. And even you can calculate the partial charges, the distribution of partial charges on the different atoms which are present in your molecule. So by knowing the partial charges, so it will help us to understand the electrostatic interaction and the reactivity of the different sites in your molecular system. See, so by performing a geometry optimization, you will get this many information. So now I'm going to demonstrate you how to perform the geometry optimization using the DFT method. Okay. So let me see here. There are one question from Chandra Prakash. Please give the idea about how to optimize the 2D structure, for example, ammonium tungstate phosphate. So here we are going to take the organic molecule in this demonstration because if I take the 2D material, so for optimization, it will take like 1 to 2 weeks in Gaussian. Okay. So that's why I can't show the 2D material. So I will go with the small organic molecule. So because if you take the small molecule, it will take very less time to perform the geometry optimization, but the procedure will be the same. Okay. So now I will just give the demonstration. So please try to do simultaneously with me. Okay. So follow each step. And if you're facing any kind of technical issues or if you're facing any kind of problem, so please write it in the chat box. Okay. So open, all of you just open the software. So you just double click on this Gauss view. So once you double click, you will get the two window, right? So this is the Gauss view window and this is the visualization window. So whatever the changes you will do here, it will be updated here. Okay. So let me fix it as a one window here. Okay. So already you know that how to use these windows. I'm not going to repeat all those kind of things now. So once you open the software, so now we need to draw the structure. So whatever the structure, for example, if you're going to perform the geometry optimization of your organic molecule, draw the structure of that organic molecule. If it is like inorganic molecule, okay, then you can open the inorganic molecule. Or if you have like so many 2D materials, in that case, you have just, but what I will suggest is like you just prepare the a slob model of your 2D materials either by using the Burai software or by using the Vesta software, and you can upload it to the Gaussian and you can perform the calculation. But you just keep in mind that you need like high-end system to perform the DFT calculation. If it is a because the time required to perform the calculation, it depends on the number of atoms present in your system. So as the number of atom decreases, it will take less time for the calculation. So when it comes to the 2D materials or metal complexes, it will take a lot of time. So better like if you have the workstation or like a supercomputer, so that is more preferable for the 2D material DFT calculation. So for this demonstration, I will go with any simple molecule. Let me take either methanol or ethanol. So let me go with the ethanol. Okay. So now we need to draw the structure of ethanol. Already you know how to draw the structure, right? So let me draw the structure of ethanol. So ethanol is a aliphatic compound, right? Acyclic compound. So to draw the structure of compound, you just click on the view, or you just click on the builder button, or click on the view button, and you just activate this builder option. So yesterday I have demonstrated everything. Okay, I hope you know all those things like how to draw the structure. So once you open this builder button, now to draw the structure of ethanol. So ethanol is CH3, CH2OH, right? 2 carbon, 5 hydrogen, 6 hydrogen, and 1 oxygen. So first we need to draw the start with the carbon. So you just click on this element fragment button, double click, select the carbon, and you have to choose this one, like 4 valency, carbon tetravalent. You just select this button. And now you see the carbon tetrahedral got selected. You just come to this window and press the left key of your mouse. Just press it here. See? So now we have drawn the structure of methane molecule, right? So, but we are going to draw the structure of ethanol. That is like CH3, CH2OH. So we have to replace one of the hydrogen with the another carbon. So what I will do here, you just keep the cursor here and click here. So now see here, now it become the ethane molecule, right? CH3, CH3, like C2H6. Now it become the ethane molecule. But I want to convert it to ethanol. So ethanol is like CH3, CH2OH. So now I will replace one of the hydrogen with hydroxy group, that is OH group. So how to do that? So you just again go to the your element fragment button, double click here. So you will get the periodic table. So now select the oxygen, and here you have to choose the how you want to draw the structure of like oxygen as a atom, or like C double bond or like carbonyl type of group, or like normal 2 valence group. You just select this one and keep cursor here, and you just click, press the left button of your mouse. So like that, you need to draw the structure of ethanol. See now, CH3, CH2OH. Okay. Now just let me close it here. So what I will do here, let me move it here. And now see here, you will get all the information here. Once you draw the structure, so at the bottom you will get total how many atoms are there in your structure. So total how many electrons are there. So what is the charge of your structure and what is the spin. So all the information you will get it here. Okay. I hope it is clear to you how to draw the structure of ethanol. Okay. So once you draw the structure of ethanol, now you need to submit the calculation. Okay. So before going for the submission of calculation, so confirm it, like just confirm me, how many of you drawn the structure of ethanol successfully? So is anybody facing problem to draw the structure of ethanol? So those who have completed, you just type Y in the chat box. Okay. Perfect. So all of you, I think you got the structure. Okay, let me go ahead. So once you draw the structure of your interest, the next thing is you need to clean your structure. Either you can call it as a clean or you can call it as a pre-optimize. Why? So because when we draw the structure, we won't maintain the proper bond angle, bond length. Okay. And if you submit that structure for the calculation, it will take more time. Let's consider, so if you clean the structure and it is taking the like 1 hour to complete the optimization, and if you submit the same structure without cleaning, it may take like 1.5 hours or 2 hours. Okay. So because it will take more time to adjust those bond length and bond angle. So that's why before submitting your structure to the calculation, so pre-optimize your structure or you just clean the structure. How to clean the structure? Very simple. You just click on this brush icon. Either you can click it directly here, or you can go to the view button and you can just, here also there is a brush button. So you just click on this button. So it will clean your structure. So once it is done, so now you are good to submit your calculation. So how to submit the calculation here? So to submit the calculation, so you just come to the menu bar here and click on the calculate option. You just click on the calculate, you will get this window. So from here you have to choose. That is a one way to submit your calculation. Otherwise, keep your cursor here and right click on your mouse. Directly here also you can go to the calculate option. Okay, see here. So whatever the menus which are present here, you can get all those menus, control, all those menus just by right clicking on this window. So here also like file menu, edit menu, everything is there. You can use any option. And now I'll just go with here, click on the calculate menu. And here you just click on the Gaussian calculation setup. That is the first option. Okay, I'm repeating once again. So once you have drawn the structures, clean your structure. So once the cleaning is done, you just click on the calculate menu. And here you will get so many options here. So you just click on the first option, that is Gaussian calculation setup. Okay. So once you click on the Gaussian calculation setup, you will get this window. Okay. So here you need to give all your input parameters. So what kind of basis set you are going to use, what type of functionals you are going to use, what is the charge of your system, what is the spin of your system, everything you have to assign here, what kind of calculation you are going to perform. Okay. So now just let's try to understand how to submit your calculation. So there are like many options are there. So now we have to go one by one. The first one is the job type. So what kind of job you are going to perform? So now we are going to perform the optimization, right? So to change the job, you just click on this drop down menu. You just click it here. So you will get many options here, like energy calculation, optimization, frequency, optimization plus frequency, IRC, scanning calculation, stability, NMR calculation. Okay. So whatever the DOT calculation you perform, the first thing you need to perform is the optimization. So once the optimization is done, so whatever the output structure you will get after the optimization, you can use that structure and you can perform the further calculation, like frequency, energy, all those kind of calculation. We'll do all type of calculation in this workshop. So here there is one more option like optimization plus frequency. If you choose this option, so it will do the optimization. Once the optimization was done, then it will do the frequency calculation. Okay. But now I just want to do the optimization. So I will choose the optimization. Okay. The first option is job type. Under that, you just select the optimization. So once you click on the optimization, you will get some option here like optimize to. There are two options. Okay. So one is like minimum state. Another is a transition state. So choose the minimum state. By default, it will choose the minimum. No need to change anything here. And like force constant. So whether you want to calculate the force constant or not. Okay. So if you want to calculate the force constant, how you are going to calculate? So there is a default option is there. Next one is like calculate at first point is there. Then calculate at all points will be there. Then read internal forces is there. Read Cartesian forces will be there. Okay, go with by default. If you go with like this, calculate at all points, so it will calculate the force constant at all point of optimization. Okay, but at the same time, it will take more time to complete the calculation. So I will go with the default option. No need to change anything here. Just go with the default option. So here, no need to change anything. Okay, so that's it. The first thing is you have to change what kind of calculation you are going to perform. Once it is done, you just click on the next tab here. That is a method tab. So click on the method. So once you click on the method, you will get these many options. So now we have to choose like what kind of DFT calculation you are going to perform here. There are many types are there. Ground state calculation is there. Zindo calculation is there. CAS is there. CL is there. Time dependent SCF is there. TDA is there. Then EOM CCSD is there. There are different types of calculations are there. Okay. So if you want to perform this ground state, you can go with by using ground state, you can perform both DFT calculation and artifact calculation. So artifact means AB initio method. So in the yesterday we have discussed that. And even by using ground state, you can perform the DFT calculation also. If you want to perform the semi-empirical calculation, then you have to choose the Zindo method. And there is like time. Usually we are going to perform in this workshop, we are going to perform two types of calculation. One is a ground state. Another one is the TDSCF, time dependent, the self-consistent calculation. Okay. So because when we perform the DFT calculation, there are two types of DFT calculation, right? So like time independent, time dependent. Then what is the difference between this time independent and time dependent? So time independent DFT calculation, when we will do for the ground state, time dependent is for the excited state. Okay. So first try to understand what is like time independent. So this time independent DFT calculation is used to study the ground state properties of your system. Okay, like if you want to find out the total energy of your system, if you want to find out the electron density, or if you want to find out the molecular orbitals like HOMO, LUMO, and other properties which are associated to the ground state of your molecule, in that case, we have to choose the this ground state, nothing but time independent DFT calculation. So it solves your like Schrodinger equation without considering the effect of time. That is what the time independent, right? So because when you study the Schrodinger equation during your master's and bachelor, so there is two types of Schrodinger equation, right? There is a derivation. So time independent Schrodinger equation and time dependent Schrodinger equation. So in the time independent, we won't consider the influence of the time. But when it comes to the time dependent, we'll consider the time factor. Okay. So here in time independent DFT calculation, the calculation will assumes that the electrons in a static state. Okay. There is no movement in the electron and will perform the calculation. But when it comes to the time dependent calculation, that is known as the excited state DFT calculation. So this type of calculation is used to study the excited state and the dynamic property of your system. So like these kind of calculations are particularly useful like for investigating the electronic excitation and response to the external fields. Okay. Or like if you want to like time dependent phenomena such as like interactions of light with the matter. If you study all those kind of things, then you have to go for the time dependent DFT calculation. And here it will use us the time dependent Schrodinger equation. Okay. It will consider the like evolution of the electronic wave function over time. So that is the main difference between the time independent DFT calculation and time dependent calculation. Okay. So very simple. See, whenever you are going to perform the geometry optimization, frequency calculation, okay, or like NMR, other spectroscopic calculation in the thermal property or mechanical property calculation, in that case, we'll go with the ground state calculation, time independent. But whenever you want to study this energy calculation, like if you want to study the transition, how the transition is taking place. So how the transition, because it is an electronic process, like electronic excitation of your like electrons which are present in your molecule. Okay, if you want to study the what kind of transition is there, and if you want to study the UV spectra, ECD spectra, in that case we need to perform the time dependent SCF calculation. I hope it is clear to you what is the difference between the time independent DFT calculation and time dependent calculation. So if it is clear to you, just type Y in the chat box. If it is not clear, then whatever the question you have, you just write it in the chat box. So you have to respond fastly. Okay, perfect. So now here we have to choose the ground state because we are going to perform the, yes, there is a question from V.S. Gayatri. Please write your question. Okay, just write it. I will take your question. So here the method is ground state. So now you just click here in ground state. Now what kind of calculation you are going to do? See, there is like mechanics will be there, semi-empirical calculation is there, artifact calculation is there, okay, DFT is there, MP2 is there, MP4 is there, CCSD is there, okay. So BD, all those kind of this is there. Okay. So now what kind of calculation we are going to do? We are going to perform the DFT calculation. So already, like yesterday in the theory, I explained that was what is the difference between the semi-empirical. So this semi-empirical is the, it will consider 50% of experimental data and 50% of theoretical data. Let me ask, I got that question. So if band gap and density of states, in this case, we have to choose time dependent SCF, sir. Okay. Yes, in case of, if you like for 2D materials, and if you want to study this band structure and density of state, we need to go for the time dependent. And time dependent and independent equations depends on the type of potential theoretically. So both the solutions will have the ground and excited state. So let me, time dependent and time independent equation depends on the type of potential. Okay, theoretically, both the solutions will have the ground and excited state. Yeah. So here in Schrödinger equation, what we will do? So we'll consider all the electronic properties. Yesterday only have explained in detail. So the difference between the actual quantum mechanical calculation and the DFT calculation. So in the Schrödinger equation, what we will do? We'll consider the each electronic part, right? The contribution from the effect of each electronic part which are present in the system. But when it comes to the DFT, we are not focusing on the individual electronic part. So we are focusing on the overall density. Okay. So that's why we are going to perform this independent equation. We are using the time independent equation. Okay. That is the main difference. That's why we are, if you derive this equation like your time independent and dependent Schrödinger equation theoretically, so we'll consider the potential. But here when it comes to, we are not focusing on the individual electronic part of the system. We are focusing the overall electronic density of that. So that's why here we will change in your DFT calculation. I hope it is clear to you. V.S. Gayatri. So any other questions? Yes, here we are not worry about the type of potential we are going to use. So automatically our job is we have to choose what kind of studies, whether you want to do the calculate the properties with respect to ground state or with respect to the time dependent like excited state. So remaining everything. So because we are using the different types of functionals and basis set, so there are some already like automated algorithms are there. So according to that, it will consider. So what are the different factors which are needed to perform those kind of calculation? Okay. So now it is like what kind of calculation we are going to use. The method is ground state. So now which kind of calculation you are going to use? You can find out the ground state properties either by using the semi-empirical method also, or artifact method also, or DFT method also, or there are some other method also there. Okay. So now in this workshop, we are going to discuss about the DFT calculation. So yesterday we discussed this semi-empirical, artifact, and DFT. So artifact is nothing but your like AB initio method. So it completely will focus on the theoretical parameters. When it comes to the semi-empirical, like it is like 50-50, 50% of experimental and 50% of theoretical. So when it comes to the DFT, it will consider overall electronic density. We are going to perform this one. So here this mechanics will be there. This is for like MD simulation type of calculation. Okay. So mechanics type of, like if you want to do the MD simulation, some electrode or batteries kind of studies, in that case, we are going to focus on the this mechanics method. But in this workshop, we are going to do the DFT calculation. Select the DFT method. Okay. So because you have to understand these parameters properly. So submitting the calculation, drawing the structure is very easy. So once you submit the calculation, software will perform the calculation and you will get the output. But this is very important, like which basis set you have to use, which function you have to use. So which polarization function or which diffusion function we have to use. So what is the meaning of that? That is very important. And the next option is like spin. So what kind of spin we are going to use here? So there are 4 options are there. One is like default spin, and next one is like a restricted spin, and next one is like unrestricted spin. Another one is like a restricted open. Now the question will come. So how to decide which spin is the best for your system? Okay. So it is very simple. If your system is like charged system, then you have to choose the unrestricted spin. So if there is a charge, either it may be positive charge or negative charge in your structure, you have to choose the unrestricted spin system. Now you may get the question, how to check that whether my system has the charge or not? You no need to worry about that. You just draw your structure here. So once you draw the structure here, automatically the software will detect whether is there any charge or not. So here it will show it here. Okay. See, totally you will get all the information. So here it is showing the neutral. So whatever the system we are going to take now, so it is like neutral in nature. Don't have any kind of charge, either positive or negative charge. Okay. If it is like uncharged system, then we have to go with the restricted spin. So if it is charged system, then we have to select the unrestricted spin. If it is like uncharged system, then we have to go with the restricted spin. Let's consider, I don't know. Even I am not able to find out that whether it is like neutral or I am not able to finding that. In that case, don't worry about that. You just go with the default spin. Then software automatically detect that what kind of spin should be considered for the calculation. Okay. In that case, it will take another 1 minute or 2 minutes extra for the calculation. And if you go with the art, if you directly give, then you can reduce 1 or 2 minutes of calculation. That is the difference. Okay. So restricted opens also some kind of times, if you like, it is a uncharged system. And sometimes people will use like restricted, sometimes they use the restricted open. So, but I will suggest you focus on these 3. And if you don't know, in all the cases, just go with the default spin. So let me go with the default one. Okay. So like what exactly happens in the restricted spin and unrestricted spin? So in your like a restricted spin DFT calculation, the same spatial orbitals are used for the both your alpha and beta electrons, right? So when we talk about this electronic, we use 2 terms like alpha electrons and beta electrons. Okay. So alpha electron is the upward electrons, beta one is the like down electrons. Okay. So like it will use both your alpha electrons and beta electrons, so which is suitable for the your closed cell electronic system. So closed cell electronic system is what? Where all electrons are paired system. Okay. So how to check that whether it is paired or not? If there is an even number of electron, then all the electrons are paired. If there is an odd number of electron, okay, so there is unpaired electrons are there. I hope it is clear to you. Okay. So what exactly happens in the restricted spin? So if you choose the restricted spin, it will consider both your alpha and beta electrons for the calculation. Okay. It is suitable for your closed cell system. So what happens in the unrestricted spin? So in the unrestricted spin DFT calculation, different spatial orbitals are allowed for both your alpha and beta electrons. So whereas in your restricted, they will consider the same spatial orbitals. So here they are using the different spatial orbital for alpha electrons and different for the beta electrons. Okay. And usually this kind of approach is suitable for your like open shell system. So open shell system means the system with unpaired electron. Okay. I hope it is clear to you. So what exactly happens if you choose the restricted spin and what happens if you choose the unrestricted spin? Okay. So restricted open spins, it is like similar to restricted only. It is quite like little bit advanced one. Okay. If you choose this one also, it is like usually it was kind of 2D materials or metal complexes. In that case, they will use. If like normal organic or inorganic complexes, molecules, in that case, we can go with the restricted. these two are like almost similar, like 99% they are similar, like restricted open, unrestricted. And there is a question like, what is the meaning of default spin? So default spin is nothing but like default option. If you don't know whether it is like restricted system or unrestricted system, in that case, you just select the default one. Okay. If you know whether it is restricted or unrestricted, then you can choose particularly that option. And let's see if you don't have any information about the spin, you are not able to find it out, then you just go for the default spin. Then software itself decide. I hope it is clear to you how to choose the spin system. So once it is done, and the next option is the here, you just click here, you have to choose. Now I have to choose the, there is, if I click here, there are many options are there. So what are these things? These are known as the functionals. So yesterday only we have discussed about the 5 different types of functionals like LDA, GGA, meta GGA, hybrid, or double hybrid functionals. Under that, they have different types of there, right? And usually we prefer, whenever we are going to perform DFT calculation, we prefer either hybrid potentials like hybrid functionals, or like GGR, meta GG. So here, like when we use this Gaussian, most of the times we'll go with the B3LYP. For this system, I will go with the B3LYP. Now the question will come. Again, see, there are many, these things are like LSDA is there, BPV86 is there, B3LYP is there, CAM B3LYP is there, right? See, there are like WB97XD is there, APFD is there. So these are the different functionals. Okay. So there are more than like 100, nearly 100 functionals are there. But they have in the software, only these functionals are available. Okay. So now the questions will come. Among these functionals, which functional we have to choose for our system? How to decide which one is best for our system? It is very simple. Let's consider if your molecular system is covalently bonded. Okay. If your molecular system is covalently bonded, then go with the B3LYP. The B3LYP is the best for such kind of system. So covalently bonded means like organic molecules. Okay. In that case, you just go with the B3LYP. And the next option. So if your molecular system is not covalently bonded, in that case, either you can go with WB97XD, okay, or you can go with the CAM B3LYP. Okay. So there is one question from the Tejaswini. So what is the uses of these functions? So yesterday only have clearly mentioned that please go through the lecture 1. I don't know whether you have gone through the lecture 1 or not. So please go through our previous session. So there we have explained everything, like what are functionals, why should we need to use the functionals, all those kind of things. Okay. So because we have to calculate how the electronic system is distributed throughout your system. For that, to calculate those things, we are going to use the functionals. Okay. I just giving the brief information. Like if you, in one word, like one sentence, if I want to tell like what is the use of functions, okay. If you want to calculate the overall electronic density of your system, then we are going to calculate them by using the functionals. So how to remember these functions depends on bonding. So why should you have to remember? There is no need to mug up. Okay. You just like, I'm just telling very simple. If your system is like covalently bonded, okay, if it is covalently bonded, then you just go with the B3LYP. So there are 3 ways, like 2 ways to decide which function is better for you. One thing is just go with the literature. The second thing is, depending if there is no proper literature, in that case you can decide. So if it is covalently bonded, then there usually people will use 2 types of functionals, either B3LYP or PBE. So this B3LYP is the GGA type of, like you can consider it as a hybrid type of functionals. PBE is the GGA type of functional. So yesterday I told like what is GGA and what is hybrid functionals. But keep in your mind, if you are going with organic molecules, okay, if you are doing the optimization of organic molecules DFT calculation, just go with the B3LYP. It is one of the best functional. Okay. If your system is like non-covalent, like for example, if you're going with some inorganic molecules or organometallic complexes or metal complexes, in that case, either you just go with WB97XD. Okay. So this is one of the functional. Otherwise, you can go with the CAM B3LYP. Okay. So CAM is like, it is Coulomb alternating method. Okay, CA means like Coulomb alternating method. So here B3LYP indicates that like Beck 3 parameters, Li Yang par. So like Beck 3, B indicates that Beck, 3 indicates like 3 parameters they are going to use. And like L indicates that Li Yang par, that is the name of the scientist. Okay. So there is a question, if choose wrong function, it will affect our calculation. Yes, definitely it will affect. Okay. If you're not going to use the proper functionals, so whatever the energy values, total energy values or parameters different like charges you're getting, it may not correct. Okay. And even let's consider if you're going to perform the geometry optimization by using the different functionals, in that case, your energy values, like overall, whatever the result you are getting, you will get the different values. Let's consider you just calculate the total energy of your system by using the B3LYP functional, and you can calculate the energy of your system by using the APFD functionals. So you can perform the calculation, but whatever the result you are getting, it will be different. So that's why you have to clearly mention that what kind of functionals and what kind of basis set you are going to use for the calculation in your paper. So there is not much difference, but there is slightly different in your total energy value. So far this B3LYP is one of the best functionals for the is covalently bonded molecules, actually like organic molecules. If it is like non-covalently bonded molecules, in that case, you just go with the WB97XD, or you can go with this one. These two are the best one. I hope it is clear to you. Otherwise, even this PBE also good for the organic molecules. So there is one more question from the Girish. How we find we are choosing the correct functions for our material? That is what I am telling now so far. First you have to decide that whether your molecule is organic or inorganic. If it is organic, go with the B3LYP. Okay. Otherwise, go with the, if it is inorganic or organometallic, then go with these options. Otherwise, let's consider if there are some literature data will be there. Okay. Someone they have used some special type of functionals and they got the good results. In that case, you can go with that. If you don't have any kind of literature already, like experimental data or literature data, then better you just go with the whatever the conditions have mentioned. We just follow those things and you can perform the calculation. I hope it is clear to you, Girish. So there is some question from Mazida. Which function is used for the performance? So that I have repeated like 3-4 times. Very simple. You just go with the WOB 97XD, or you can just go with the CAM B3LYP. I hope it is clear to you, Mazida. There is one question from Bhargav. What if the compound mixed of both organic and inorganic? Yes, if it's mixed of organic and inorganic means how we'll consider it is a organometallic, right? So organometallic means it is a non-covalent bonded. Then you can go with that. Bhargav, is it clear? In that case, it is considered as a organic organometallic molecule. Okay. In that case, you have to go with these kind of things. I hope it is clear to you how to decide this functional. Okay, if it is clear, now let's go to the next option. So for this calculation, I will go with the B3LYP. But please write it your question, okay? Whatever the question you have, you just write it in the chat box. You have to understand each parameters clearly. Okay, so now here, next is like basis set. Let's talk about the basis set here. See, if I click it here, there are different types of basis sets are there. Like STO 3G is there, 321G is there. If you read the papers, most of the time people will mention that like 321G or 631G or 631G or 6311G. So these kind of basis set they have used. So here also you have to choose the basis set properly. Again, you will get the question like how to choose this basis set. Right? So how to choose this basis set? So in this case, I am just going with like you can choose any kind of these things, but there is I will give one trick to you how to choose that. If your molecular system have like metallic atom. Okay, so metallic atom is like metal complexes, organometallic complex. If it contain any kind of like transition metals like iron, nickel, copper, cobalt, palladium, platinum, okay, zirconium. There are in that case, you just go with the these two. There is a two best, yeah, this one, this LAN L2DZ, or you can go with the LAN L2MB. These two basis sets are like good for the your like metallic compounds. Okay. And if your molecular system does not contain any kind of like metallic atom, in that case, you can go with this, either 321G or 631G or 631G star or 6311G. Okay. I'm repeating once again. So see, there are many basis sets are there. So among these basis set, which basis set is good for your system? How to decide? Very simple. If your molecular system have metallic atom, metallic means like metal complexes are organometallic. In that case, these two are the best one, like LAN L2DZ or LAN L2MB. Okay, for metallic system. If your molecule system does not contain any metallic atom, means for organic molecules, you can choose any one like 321G, 631G, or 631G star or 6311G. So you may get the question now, among these four, which one is the best one? So this one, like 6311 is the best one. But at the same time, you have to keep in mind that, so if you use this, so this is the accuracy level order. Okay, I will talk about what is this three number, like 32 indicates that, 631 indicates that, what is the meaning of that number. I will talk later. Now first understand, among these four, so this one is the best one, 6311G. So it will give more accurate result. Okay, at the same time, it will take more time to perform the calculation. Just to reduce the time of calculation in this demonstration, I will go with the 631G. Okay, I will go with the 631G. I hope it is clear to you. And you may get the question like here, there are other is there like, you can also use this for like solid materials. So depending on that, sometimes what happens, even if you're like your metallic system, like metal complexes, and you are going to use these two like LAN L2DZ or LAN L2MB, then also you won't get the result. Sometimes your calculation will die. Okay. Because in your system, there are both compounds are there. Like metal atom is also there, non-metallic atoms are also there. Okay. In that case, what you need to do, you have to use the mixed basis set. Mixed means instead of using only one basis set, so you have to use the multiple basis set, either two basis set or three basis set. So one basis set for the metallic atom, one basis set for the non-metallic atoms. I hope it is clear to you. Okay. So then you will get the question. See here, whenever you are going to submit the calculation by using the Gauss view, so you can choose only one basis set at a time. Then how to give the multiple basis set? In that case, we have to use the Gaussian. Directly, you have to prepare input file and you have to submit the calculation directly to the Gaussian software. Okay. So first you just learn how to perform the calculation by using the single basis set. So on the fourth day, so I will demonstrate you how to perform the calculation by using the multiple basis set. Okay, like if you have like transition metal complexes, how to do that, and we'll go later. First, we'll understand the basic part. Okay, so again, now the question will come. See, there is like 321G is there, 631G is there. So what is the meaning of this number? What does this meaning indicate? So yesterday, while talking about the basis set, I have told you that what is the use of basis set? So by using the basis set, we are going to determine the shape of the orbitals, right? So we are going to describe the shape of the atomic orbitals. And like how we can describe, there are two types like GTOs and STOs, Gaussian type of orbitals and slatted type of orbitals. And yesterday I had told that, so we are going to calculate the Gaussian type of orbitals instead of slatted type of orbitals. Why? So because computing Gaussian orbital is quite easy. It will take less time compared to the slatted type of orbitals. So that's why we are going to choose the Gaussian type of orbitals. Okay, so these are like Gaussian type of orbitals. Here the alphabet G. So see here, G is common, here also G is common. That G indicates that it is a Gaussian type of orbital. That is the meaning of the letter G. Then what does this number like 6311G? Okay. And like how we are going to assign the orbitals? See, whenever you can take any kind of system, so how we are going to consider there is a core orbital, right? Pure inside there is a first core orbital will come. After core orbital, there will be the inner valential orbital. After that, there is a outer valential orbital, right? You can take any system. So you have the core orbital, then you have the valence orbital. In valence orbital, you can consider inner shell valence orbital and the outer shell valence orbital. So here, the number 6, the first number, either 3 or 6, or here 6 indicates that So there are total 6 Gaussian type of orbitals for the core orbital. Means this basis set will use 6 type of Gaussian orbitals to calculate the core orbital. Okay, that is the number of meaning of that number. Then what does it indicate? So here 3 indicates that. So this basis set will use 3 Gaussian type of orbitals for the inner valence electrons. Okay. Then what does this 1 1 indicates? Okay. They don't have separate meaning. So this 2 1 1 indicates that. So here it uses 2 different types. So 2 different types of Gaussian type of orbitals for the outer valence electron. I am repeating once again. So here in G indicates that the type of orbital, whether it is a Gaussian or slatted, here G indicates that Gaussian type. If it is like ES, it indicates like slatted type. But in the Gaussian, we are going to use the Gaussian type of orbitals only. And here the number indicates that when you talk about the any system, there is a like core orbital and the valence orbital. And the in valence orbital, you can consider it as the inner valence shell and outer valence shell. And in the core orbital, some electrons are there. Inner valence orbital, there are some electrons are there. In outer orbitals, valence orbital, there are some electrons are there. Okay. So here, the number 6 indicates that. So this basis set is using 6 Gaussian types of orbitals to calculate the properties of the electrons which are present in the core orbital. Okay. So it is using the 6 GTOs. All the 6 GTOs are same in nature. Okay. That is the meaning. And the next number 3 indicates that it is using 3 GTOs, 3 Gaussian type orbitals to calculate the properties of electrons which are present at the inner valence orbital. Whereas this 1 1 indicates that this basis set is using 2 GTOs. Here it is using 2 GTOs. Those 2 are like different from each other. Here like all the 6 are one type, all the 3 are similar to each other. But here 1 1 indicates that it is using 2 Gaussian type orbitals, but those 2 are different from each other. And what is the role of these 2 GTOs? It will calculate the properties of electrons which are present at the outer valence orbital. So that is the meaning of that number. I hope it is clear to you. Okay. For this calculation, just to keeping time, I'm just going with the 631G. So is it clear? If it is clear, you just type Y in the chat box. If there are any questions, please write it in the chat box. Okay, perfect. Now let's move on to the next one. So what is the next option here? See, if I click in this down arrow button, there are 2 symbols are there. One is there is nothing. There are 3 options are there. One is like nothing. Next one is like plus. Next one is double plus, plus plus. So what is the meaning of like nothing plus double plus? When we go with nothing, when we go with the 1 plus, when we go with the 2 plus, what is the exact meaning of that? That is very important, right? So because when you see the papers, they have mentioned that. So we have performed the calculation by using the B3LYF functional 631G plus D like kind of basis set. They have mentioned that. Then what is the meaning of this plus plus? So yesterday while discussing the basis set, I discussed about the 2 things. One is like diffuse function basis set and the polarization function basis set. Okay. So it is known as the overall these terms are known as the diffuse functions. Okay. So later I will talk about what is exactly diffuse function. Why should we need to use a diffuse function? First, let me talk about these terminologies. Okay. So these things indicates the diffuse function. Here the plus. Okay. Here the plus indicates that the diffuse functions are added to heavy atoms which are present in your basis set. Okay. So what is a heavy atom? So heavy atoms means non-hydrogen atoms. Okay. So if you choose the plus, it indicates that the diffuse functions are added to the heavy atoms which are present in your system. So if you choose the plus plus, double plus, it indicates that the diffuse functions are added to both heavy atoms, okay, and non-heavy atoms in your system. So whenever I will tell like heavy atoms, those are like non-hydrogen atoms. So when I will call it like non-heavy atom, those are considered as the hydrogen atoms. So that is the meaning of plus and double plus. So whenever you are going to choose plus, it indicates that you are going to add the diffuse function only on these heavy atoms like non-hydrogen. Let me keep it as like hydrogen and non-hydrogen atom. Then it will be clear to you. So only on the non-hydrogen atoms, means atoms other than hydrogen. Whenever you are going to choose double place, it indicates that you are going to add the diffuse function both hydrogen atom and non-hydrogen atoms. Overall, all the atoms which are present in your structure. Okay, so that is the meaning of that. So if you choose nothing, it indicates that you are not using diffuse function in the calculation. You are not adding diffuse function on any kind of atom, either it may be hydrogen atoms or non-hydrogen atom. You are not going to add the diffuse function. I hope it is clear to you. So when to choose nothing, when to like what is the plus and what is the double plus. If it is clear, you just type Y in the chat box. Otherwise, if you have any questions, please write it here. Perfect. Okay. So now I'm talking about like plus, double plus, nothing, and when to use that. Now the question will come. So because I was just telling like diffuse function, there is even question, what is empty? So empty means we are not using diffuse function in the calculation. So we are not going to add the diffuse function either on hydrogen atom or non-hydrogen atom. We are not considering the diffuse function. That is the meaning of that empty space. Okay. Now let's try to understand what is diffuse function. So diffuse functions are the basic functions. So with like they have like small exponent. Okay. So means like they are like spread in your space. For example, if there is a diffuse function, so these functions will be spread in your system, like in the space. So why we need to use this diffuse function? Because these functions are essential to accurately describe the electronic structure of, especially if there is kind of anions. If you are going to perform the DFT calculation of anions, or if you are going to perform some excited state, or if you are going to perform like a system where electrons are like delocalized over the large region, such as like if your molecule with like lone pair of electrons are weakly bound complexes, in that case, we have to use the diffuse function. If you don't use the diffuse function, so because this charge is widely spread in the space, then you won't get the accurate result. So to avoid that spreading, we are going to use the diffuse function. So especially if your molecular system contain like anions, or like if you are going to perform say excited state calculation, or if there is kind of like lone pair of electrons, or like there is weakly bound complexes, in that case we have to consider this diffuse function. Now here also we have the lone pair of electron, right? So we have the oxygen, and oxygen has the lone pair of electron in it. So that's why you have to use the diffuse function. So when we need to use the diffuse function, when your system is like charged, like especially when it has the anions, like negatively charged ions. Now, when you are going to perform the excited state calculation, another one is like there is a lone pair of electron or weakly bound complexes. So why we have to consider this diffuse function when during the anions? Because your anions have the extra electron, right? So because of that extra electrons, what are the extra electrons present on your anions? Those are like weakly bound, and it will spread out. So while during the calculation, geometry optimization, it will spread out. Okay. So to avoid that spreading of electron in the space, we are going to use the diffuse function. So when you use the diffuse function, it will avoid the spreading of that one, and it will perform the DFT calculation with proper representation. Similarly, in excited state calculation, the electrons are often in like higher energy orbitals. So when the electrons are at higher energy orbitals, which can easily spread out in the space, to avoid that one, we are going to use the diffuse function. Okay. And now let's consider if there are like weakly bound complexes, like you are going to perform some like metallic complexes, or there are lone pair of electrons there. Okay. So there also there is a weakly bound because the distance is very high. Because of the larger distance in your metal and the non-metallic atoms, so it may undergo the spreading. So to avoid that one also, we are going to use the diffuse function for the proper calculation of your energy, or whatever the different types of calculation you are going to do. For that case, we are going to choose. I hope it is clear to you. Okay. Okay. If it is clear to you, okay, you are telling why. So, okay, fine. Now I have explained properly what is the diffuse function, and when we need to choose the diffuse function, and why we need to choose the diffuse function, and what is the meaning of this place and double place and this empty space. Now, can you tell me that Which diffuse function we need to use for this type of this calculation? Okay. So there is a question, there is an answer from V.S. Gauri plus Dr. V.S. Gauri plus. Okay. Any other answers? So you have to be interactive. Okay. You just tell whatever you are feeling, you have to tell that. Okay. Plus. One, Yamin is telling that plus. Okay. Any other answers? There are only three options, right? Either plus, double plus, or empty. And the correct. Okay. So Akshay Kumar plus DT. Okay. Marutavani, okay, MT. Chandra Prakash plus, Rakesh plus, Sachin Kumar KB plus, okay, Mazida plus. And the correct answer is we have to go with the plus only. Not MT, not double plus. We have to go with the only plus. So because what is the meaning of plus? It indicates that like where you are going to add the diffuse function. So if you focus on your structure here, so what I said, we need to use the diffuse function either if there is a anions, or if you want to go to perform the excited state calculation, or if you want to perform the weakly bound electrons or lone pair of electrons. If you take this structure, so this is carbon, this is also carbon, these are hydrogens. These carbon and hydrogen, they don't have either any kind of charge, even they don't have any kind of lone pair of electrons. Here only the oxygen, which has the lone pair of electron. So now we have to protect this lone pair of electron from spreading in the space, right? So this is oxygen. Oxygen is a non-hydrogen atom. So if it is a non-hydrogen atom, if you want to apply the diffuse function only on the non-hydrogen atom, then we have to choose the plus. I hope it is clear to you. Okay. For this system, we have to go with the plus option. Now we may get the question. What if I go with the plus? Okay. So like for this system, I need only plus, right? But instead of that, I will go with the plus. What happens then? Do I get the wrong answer like calculation? No. Even by using the plus also, you will get the accurate result only. But the time it will take more time, because even if you choose plus, now it will add the diffuse function on all the atoms. Even though there is no lone pair of electron, nothing is there. So nothing will happen, you will get the result. But the proper one is like this one, plus. And if you want to go with the plus, nothing will happen. But don't go with the nothing. If you go with this empty option, then whatever the result you are getting, it may be not accurate. Okay. Yes, it is time consuming if you go with that plus. And there is a question from Sachin Kumar, what happens when don't? So when don't means? Yes. Yeah, your question is what happens when if you don't select any kind of diffuse function. That is what I said. If you didn't select any kind of diffuse function, then whatever this lone pair of electrons which are present on the oxygen during the optimization, it will spread. So here lone pair of electrons are here, lone pair of electrons are there, right? It may spread out. And because of that, it won't give the proper energy value. Okay. I hope it is clear to you. And there is a question from Rakesh, carbon also non-hydrogen atom. Like you are asking, it is non-hydrogen atom, right? Yes, it is also non-hydrogen. So non-hydrogen means other than hydrogen, all the atoms are like non-hydrogen. Okay. That is what the meaning of that non-hydrogen. So don't consider like how many hydrogen, whether hydrogen is attached to carbon, or you just don't focus on that. So because here participants, most of the participants are from physics background, other background also there. So you may get these kind of questions. Okay. No need to worry about that. Whatever the question you have, you just write it here. So non-hydrogen atoms means other than hydrogen, whatever the atom it may be, either it may be nitrogen, oxygen, carbon, anything. Those are considered as the non-hydrogen atom. I hope it is clear to you. Rakesh. Okay. So now let's move on to the next option. I hope it is clear to you. Okay. If you click here now, so now there is some options are there. Like there are some options are like empty space, is there nothing? D, 2D, 3D, DF, 2DF, 3DF, 3D, 2F is there. And if you select it here also, like here, like D is there. Here it will start from the P. Okay. So what is the meaning of this? These two boxes. Okay. So whatever the things we are choose here in these two boxes, we'll consider it as a polarization function. So this is a diffuse function. This is a polarization function. This one is also a diffuse function, polarization function, and this one is also the polarization function. Okay. So now here I will go with the D option. Here I will go with the P option. See here, first one is empty, remaining like D, 2D, 3D, DF, 2DF is there. So here I will choose the D here. And here like there is many options are there. I will go with the P option. So now you may get the question. So how to decide whether it is like D or 2D or 3D or P or 2P? How to choose that one? What is the meaning of that? So I said that there is a polarization function. So now you need to understand what exactly this polarization function. Okay. So when we need to choose the D, when we need to choose the P. Okay. So first I will tell that what is the, see here all the terms are in terms of like D, right? It is starting from D. Here all the terms are starting with P. So what is the meaning of this D polarization function and what is the meaning of this P polarization function? So here D polarization functions, okay, indicates the, like these are the polarization functions which are added to the non-hydrogen atoms. So because here we are adding the polarization function, in your atoms there are two types of atoms, like hydrogenic atom, non-hydrogen atom. And if you want to add the polarization function to the non-hydrogen atom, in that case you have to choose the deep functions. Okay, so here the P function indicates that polarization function added to the hydrogen atom. I hope it is clear to you. So see, there are many D functions are there. So these functions indicates that we are going to add, if you choose any function here, so it indicates that we are going to add the polarization function to the non-hydrogen atoms which are present in the your system. Okay, so if you choose any kind of P functions here, it indicates that, so we are adding the polarization function to the hydrogen atoms which are present in your system. I hope it is clear to you what is the difference between the depolarization function and these P functions. Later I will talk what exactly the polarization function, then what is the role, why should we need to use. First try to understand these things. I hope it is clear to you the difference between the D functions and P functions. Okay, so D function is we are going to add the polarization function only for the non-hydrogen atom. Okay, so P function is for we are adding the polarization function to the hydrogen atom. So that is the difference between the D functions and P functions. So now you may get the question, like see there are different types of things are there, right? If you choose here, there is empty. If you choose this option, it indicates that, so we are not adding polarization function to the non-hydrogen atoms. And if you choose empty here, it indicates that, so we are not adding any kind of polarization function on the hydrogen atoms. I hope it is clear to you. Now let's consider, see there are different types of functionals are like D functional, 2D functional, 3D functional, DF. So what is the meaning of that? So if you choose only D, it indicates that, so it will use only one set of D type of polarization function. Okay, so 2D indicates that two set of D type of polarization function. Okay, 3D indicates that it will use the three set of D type of polarization function. Okay, so next one is the DF. DF indicates that it will use one set of D type function and one set of F type function. Okay, and it's all the functions we are applying for the non-hydrogen atoms. And what about the 2DF? 2DF indicates that it will use two set of D type of functions and one set of F type of function. Similarly, the 3DF indicates that it will use three set of D type of functions and one set of F type of functions. So whereas this 3D2F indicates that it will use three set of D type of functions and two sets of F type of functions. That is the meaning of those terms like D, 2D, 3D. Okay, those are like not orbital. Like when we talk about when we write this electronic configuration, 1s, 2s, 2p, those are not kind of orbitals. Okay, so this like what kind of functions it will use for the polarization. I hope it is clear to you. Similarly, if you come here P indicates nothing, means we are not going to add anything here. And here we are going to add like P. Okay, so here like P indicates that one type of P polarization function. So 2P indicates that it will use the two sets of P type of polarization function. Here, three sets of P type of polarization. It indicates that PD indicates that one set of P type polarization and one set of D type functions. 2PD indicates the two set of P-type functions and one set of D-type functions. Similar, like how I explained this one. If you go with like 3P2D, it uses three set of P-type and two set of D-type. I hope it is clear to you. Okay. So now the question will come. So when we go with what, how to choose? For example, like small organic molecules. So D function is sufficient. Like here, like there are many are there. Now the question will come. So when to choose D, when to choose 2D, when to choose 3D, how to decide which is good for your material, right? For example, if you have like small organic molecules, so for that, D function is more than sufficient. Okay, let's consider if your system contains some anions. Okay, otherwise your whatever the system you're going to consider it is very large. Okay, so in that case, you may require like higher functions like 2DF, DF, or 3DF. Okay, and let's consider if you have like transition metal complexes. In that case, even you need more higher diffuse function like 3DF, 3D2F. Okay, so very simple. So if you have the organic molecules, simple organic molecules, in that case, you just go with the DR2D. That is more than sufficient. Okay, like DR, 2D, or 3D, depending on the number of atoms. For this one, D is more than sufficient. Like if you have your system has some kind of like anions, or there is some kind of lone pair of electrons, or if you're using like very large molecule, in that you have to use some higher like DF or 2DF. If you are going with like transition metal complexes, in that case, you just go with the 3DF or 3D2F. Okay. Similarly, if you come here, so for like organic molecules, like P, 2P, 3P is more than sufficient. And if there is like some kind of like larger molecular systems or metal complexes are there, in that case, you have to go with the heavy one, like 2PD, 3PD, 3P2D. Okay. So for this ethanol molecule, which one is good? Can you write it now if it is clear to you? Can you write it now which D function we have to use and which P function we have to use for this molecule? Just write it in the chat box. I hope it is clear to you because I'm explaining each point. Okay. So, okay, D and nothing, DP. Okay. DP. Okay. Yeah, perfect. Okay. So here we are going to use the DP. D, and here we are going to use the P. So D and P is the best option. Why? So we are going to add the depolarization function for the non-hydrogen atom because our system contains both hydrogen and non-hydrogen atom. So for hydrogen atom, we are going to use the D1, and for non-hydrogen atoms, we are going for non-hydrogen, we are going to use the D1. For hydrogen atom, we are going to use the P function. I hope it is clear to you. Okay, if it is clear, let's move on to the next point. Next one is the charge. It is very simple. You no need to worry about here, like how to choose the charge, all those kind of things. So because it is very simple, right? So because automatically it will show. If you see here, it will show whether it is like positively charged or negatively charged. If it is positively charged, what is like whether it's +1, +2, or +3, or if it's negatively charged, it will show whether it is -1, -2, -3. If it is nothing, then it will show neutral. And this ethanol is neutral, so I will go with the 0. If you want to include a positive charge, negative charge, you can just click it here, like it will give negative. But our system is the neutral, so I will go with the 0. And the next one is like spin. Okay. So how to select the spin here? So like here, if you click here, there is a singlet, triplet, quintet, septet. Okay, there is different types of spin is there. Automatically it will show here. You no need to worry about that. So just see it here, and you can just select it. What kind of is it? So it is like spin means multiplicity. So what kind of multiplicity, whether it is like singlet, doublet, triplet. Okay, you can choose that. If you are from chemistry background, you can easily just by seeing the structure, you can easily predict whether what is the multiplicity. Otherwise, if you are from physics background, you can just use this knowledge. It will show it here, whether it is showing it is a singlet. So I will go with the singlet. Okay. So once it is done, now let's go to the next option. I hope it is clear to you, right? So I hope you're done with all these options. So now nothing to do it here. So now we just click on the next one is title. Okay. Just click on the title tab. So now just give the title for your calculation. So what kind of calculation we are going to do now? Now we are going to perform the optimization. So what I will give? So I will give the name of the compound and I will just give the optimization. It is up to you, can give whatever you want. I'll just give the ethanol underscore optimization. Okay, so ethanol underscore optimization. So once you are done with title, You just click on the next tab, that is link 0. So here you no need to do any kind of changes. But if you want to see, like I don't want to show this option now itself, because like if you want to increase the speed of your calculation. Okay. So in that case, you can just go here and you can assign how much memory you want to use for that calculation. Then how many processors you want to use. Like consider if it will go with the default, it will use the default processor. Otherwise, if you want to specify properly, then it will choose how many. Like it depends on like how many processors you have. So before that, you have to just, if you click on the specify and you just like consider if you have just 10, you can give it like, let's consider if your system has like 16 processor, and you can give that, let's consider like keep it as 3 to 4 for your for other calculation, and keep it like 10 to 12 for the calculation. Then you can increase the speed of your calculation. Okay. But I will just go with the default option. I don't want to change anything. So there is a question from Sachin Kumar. So top right corner, one option is there. Multi-layer onion model. What is that, sir? So where? Top right corner. So I was not able to see it here. Yeah. Okay. So here in the method, right? So it is for like 2D materials. Here I will talk about when we do like separate calculation. I will explain. Okay. So for this one, optimization is not treated multi-layer onion on this like onion model. So in the later calculations, I will explain this option. When it comes, I will explain. No need to worry about that. I will cover each part of the software. You no need to worry about that. Okay. Title, then come to the link here. No need to do anything here. Okay. And you just click on the general here also. You no need to, for this calculation, no need to do anything. So, okay. For optimization, no need to worry about that. And you just click on the guess here also, no need to worry about anything. And then like here is a population here also, you no need to worry about anything. Okay. For this calculation, geometry optimization. So for other calculation, we have to do little modification. For this one, not needed. Then PBC, like periodic boundary condition, it is useful only for the 2D materials. So no need to worry for the small molecules. Then if you come on the salvation, so it is very important here. So how you want to calculate the energy? See, so let's see, when we calculate the energy, if you read the paper, they have mentioned that like gas phase energy, and they will mention that some specific of solvent energy. So let's consider if you want to perform the gas phase energy, so you have to perform the optimization without any solvent. That is a none option. Usually we'll go with none. Okay. Let's consider if you want to find out the total energy of your system in presence of some solvent. What is the energy of your system when you add it like water? What is the energy like with other solvents? In that we have to choose the like respective solvent. How to choose the respective solvent? You just click here, and there are different models are there to choose like what kind of model you want to use. Just click on the default one. Click on the default one. Once you click on the default one, so here it will give the option to choose the solvent. So here you can choose the water, DMSO, nitromethane, acetonitrile, methanol. Different types of solvents are there. You can use it for the calculation. Okay. But in this calculation, I will go with the none, because I want to perform the optimization in gas phase. So I will go with the none option. So if you, in your case, if you want to do calculate the energy in specific solvent, then you can choose the solvent there. Okay. And then you just click on the additional inputs. If you want to give anything, you can just write your additional input, but I don't want to write anything. And once it is done, you just click in the preview button. Once you click on the preview option here, so here get like all kind of what is the given, like it will show it here. So what kind of calculation you are going to perform? See, you are going to perform the optimization. What kind of like function you are going to use, like basis set like B3LYP/631G plus G like D comma P, and we are going to use geometry connectivity, and this is the different parameter like coordinates of all the items which are present, X coordinate, Y coordinate, Z coordinates. You will get all the information here. And now we are done with the input parameters. And now before submitting the calculation, we have to give an additional keywords at the bottom. See here, if you see here, so you have to write one additional keywords. Now this update button is not active, it is inactive now. So once you give the keyword, it will activate now. Okay. So whenever you are going to run this calculation, you have to write on keyword that is pop is equal to full. Otherwise, sometimes you will end up with the error. Your calculation will die in between. So you have to write the keyword pop is equal to full. POP, pop is equal to full. That is the keyword. But don't ask me what is the meaning of pop is equal to full. I don't know. So it was like they have designed software like that in their procedure manual. They have mentioned that whenever we run this calculation, we have to give this keyword. Okay, pop is equal to full. That is a keyword. So once you have written that additional keyword, you just click on this update button. Okay, so you just click on this update button. Once you click on this update button, see, it will update that keyword here. So previously we don't have this keyword. So only we have the geometry is equal to connectivity. Now once you click on this update button, it will add that keyword here. Pop is equal to full. So once it is done, so now we are good to submit the calculation. So to submit the calculation, you just click on the submit button. Okay, so click on the submit button. So once you click on the submit button, you will get this message. So you must save a Gaussian input file before you submit. Would you like to save an input file now? You just click on the yes button. So once you click on the yes button, this window will pop up here. Okay, so here you can just choose the location where you want to save your calculation. So by default, it was chosen in the downloads, but I want to save it on the desktop. I will choose the desktop folder here, and I will give the file name here. So I will just give my input file name as ethanol. I will just give the same name, ethanol underscore opt, ethanol underscore opt, and just click on the save button, and it will save your input file in the format of like .gjf. Okay, and you just give this name, whatever the name you have given in the title, you can give that same name, and you just click on the save button. So once you click on the save button, it will ask you to submit the following file for the Gaussian. Okay, so far we are inside the Gauss view. Okay, so now once you click on the yes button, it will submit this input file to the Gaussian software, and it will start the calculation. You just click on the yes button. See, once you click on the yes button, it was activated Gaussian. See, now the Gaussian 9 version, 09 revision. So now the calculation is going on. So now it will take some time to complete the calculation, and the time required for the calculation depends on the number of atoms which are present in your system. Okay, and the type of input, like parameters you have used, like basis set, functionals, diffuse function, all those kind of things. And it also depends on the your system specification. Okay, so there is one question from like Marutavani. Explain once again, sir, after salvation. It is quite difficult because already we are running out of time. So I need to cover a lot of things now. So please, you just go with the recordings, okay? So because otherwise I need to run the calculation. So in my case, the calculation was completed. So once the calculation was completed, you will get this kind of window. So Gaussian job has completed. So do you want to close the Gaussian window? See here, what happens? Okay, so what happens here? See here, now it took only for me around like 1 minute, right? So because this almost whatever the structure you have given, like bond length, bond angle, almost proper. Okay, and there is it is like very simple structure. There are only 9 atoms. That's why it is taking very less time. If you take the bigger structure, it will take more time. Okay, so for demonstration, I can't go with the like larger complex or like metal complexes or like 2D materials because it will take a lot of time. So that's why I'm just explaining the entire procedure by taking the small molecules. So before going to the analysis part, so can you confirm me that how many of you completed the calculation successfully? So Amini got error. So can you please share the error, whatever the error you got, Amini? Okay, Amal done, Gauri done, okay, Rakesh done, Mazida, Chaitra, Bhargav, Chandra Prakash. Okay, most of the participants, they have executed the calculation successfully. Ankita still running, okay, fine. So what about others? So you need to respond because it is an online training program and a hands-on training program. At least we have to keep the interactions. Otherwise, it is quite difficult for me whether you are understanding or not. Okay, no problem. It will take time depending on your system specification. It will take some time, like 2 to 3 minutes. Okay, so I will wait for 1 minute. So because still it was running in many participants system. So because we have to start the analysis part. Analysis is also very important. The main thing is calculation software will do. The important thing is how you prepare your input file and how to submit the calculation. And the second thing is once your calculation was done, how to interpret the data, how to extract the information which is needed for your work. That is very important. Because even if you go to the YouTube, there are many tutorials you will find that. There they will tell that, okay, submit the calculation, select. But no one will explain what is the exact meaning of that. Why should we have to take? You have to understand that one. So Sachin Kumar Gaussian is already running, sir. Means, yes, it will. Okay, it is calculation is doing, I think. Let me check this one. So installation corrupt in or incorrect installation. I think, ma'am, in your case, the installation was not done properly. So you just do one thing, you just uninstall your software, okay, and create the proper scratch folder and you try to install the software in the C drive, okay. Now you just uninstall the software and you just go to the your program files. There will be one folder with the name like Gaussian. You just delete that folder and there will be another two folders in your C drive with the name like G9W something and one more something like another like let me show it here. There are two folders. You just delete that folder also. So let me, if you open it here, you will just go to the C drive. You just delete these two folders, G09W and G16W, these two. And then you just go to the program files also and you just delete this one more folder. You will get something here like Gaussian. The first thing is you need to uninstall your software. Once you are done with the uninstallation, you come to the C drive and just delete these two folder and just go and open your program files. Here you will get one folder called like a Gaussian. I think it is not there. Let me check it in the program 86, this one. Yeah, I think Gaussian here is also not there. Let me. Yeah, I think it is not there. Only I think these two folder only. Okay, you just delete these two folder completely and just restart your system and you just install it. I think then it will solve your problem. So any other participant facing any kind of technical issues? I think now the most of the participants have completed the calculation, right? So previously those who have mentioned that still it is running. So whether it is completed or not. Okay, so let's start with the installation part now. Okay, so what I will do now here, I'll just, okay. So once your job is completed, you will get this kind of message. Like your job was completed successfully. Like, do you want to close the Gaussian window? Okay. So if you click on the yes button, it will close this Gaussian window. If you click on no, that it will won't close. You just click on the yes button. Okay. You just click on the yes button. So once you click on the yes button, this window will pop up with the name like open files. Okay. So once your job got completed successfully, it will create two files. Okay. It will create two files. One file, like whatever the name you have given with the same name, one file in the .chk format, extension format. Another one is the whatever the name you have given plus .log file. So this is the logarithmic file. This is the chk file. So chk is nothing but checkpoint file. Okay, that is a short form of checkpoint file. Okay, so now we need to do the we have to analyze the output data results. So in these log files, you have all the information. Now, if you want to calculate these values like energy values, total like charges, partial charges, or Mulliken charges, or if you want to calculate the dipole moment or vector, and all those kind of things, we have to use the logarithmic function. And if you want to draw this kind of like optimization curve, like energy optimization curve, different curves, in that case, we have to use the chk file. But now don't open the chk file. So now we are going to do the analysis by using the logarithmic file. First, all of you just open your logarithmic file. Select logarithmic file, you just uncheck chk file, just select this one. Okay. And you just click on the open button. Click open. See, it will open the logarithmic file. See, it is the structure before optimization. So this is the structure what you got after optimization. See, I hope it is clear to you. So this is the structure before optimization and this is the structure after optimization. So you may ask now, so what is the difference? Both are looking same, right? There is nothing different. Then why should we need to perform the geometry optimization? So here you won't find, if you see directly like this, you may not find some difference between them. Okay. So if you want to see the difference, in that case, you have to analyze their different charge distribution, all those kind of thing. I will show it here. So first you open the structure. The first thing you need to do is Let me minimize this one. Okay, so this is your structure. The first thing you need to do is you just save this structure in the image format, and you can use it for your uh, paper or report. How to save this? You just right click, and here you can just go to the file, and you can just click on the save option also here, and you can choose what kind of file you want to choose here, like all file format, and you can save it in the PNG format. Okay, otherwise there is a TIFF format is also there. One more option is there here. Let me right click here, then go to the file edit option is there, edit. Let me show it here, tool, results, calculate, view. Okay, builder. Okay, so here before going to that, you can change the different format here. Let me show you. Right click, go to the view, and go to the display format. And you can just here, you can just represent your structure in different format here. As already yesterday explained that, you can just do format like ball and stick, and you can ball and bond type, or you can just wireframe. You can represent your structure in different format. And let me go with the ball and stick here. Okay, and you can just go to the quality also. You can increase the realistic model. You can increase the quality also, and you can change the background also. For publication, either you can keep like white background, or you can keep the black one. If you want to keep it in your paper or report, I will suggest either white background or black one. Okay, so you can change this one also. And if you want to give some test also, you can just change like font style, font size, and color of your font, all those kind of things. And you can surface, like what kind of surface you want, like solid mesh, all those kind. Here you can't find this difference. I will explain this surface option later. Okay, apart from this, and here you can whether you want to show the hydrogen or not. See, if you deselect it, it won't show only, it will show only the non-hydrogen atom. If you want to show the labels, you just select this option. See, it will label, it will give the position of the atoms, like what is the numbering position of that one. And then if you click on this, if you don't want to show the bonds, see, it will go the bonds also. And here, if you want to show the stereochemistry, there is nothing. If there is some stereochemistry, it will give the stereochemistry also. And if you want to show the symbols, like what kind of whether it's like oxygen, carbon, hydrogen, in that case, you just click on the show symbols. Okay, then you can just, it will show. You see carbon 1, carbon 5, it indicates that the first position, it is present at the 5th position. So like that, you can give that one. And if you want to show the Cartesian axis, you just click here and see, it will give the Cartesian axis in the block color. So let me change the color here, then you can easily find out that visualize the Cartesian axis here. See, so what is like X, Y, Z axis, like it will give the Cartesian axis also. And this is like positioning tool. Here it will give like, you can change the position along, like rotate. If you want to rotate, how you want to rotate your structure, like here you can along, if you want to visualize your structure along the XY plane or YZ plane. Okay, in that case, you can use this position tools. Otherwise, no need to use. Even I don't want this Cartesian also. Okay, so this one is fine here. So there is question from Akshay Kumar, how to do Mulliken chart. Yes, I will come. Okay, one by one I will come. No need to worry about that. Once it is done, let's consider this like general settings. You just click here, and then here, tools, options, edit file, or you can go to the file option. Yeah, you just click on the save image. Okay, if you want to save it in the TIFF format, either you can click on this camera option like save image, and you can just see, now you can save it in the TIFF format or JPG format. You can your option, go with this option. So now just come back here. So once it is done, so now we want to do the actual analysis. So if you want to do the analysis of your result, you just right click here and go to the results. Otherwise, you just click on the result tab here also. Otherwise, it is very simple. You just keep your cursor on your log file. This is an optimized logarithmic file. I hope you are following me, right? So I think most of the participants, they are doing simultaneously with me. So reading file, see, download, Satana optimized log file. I think it is from Marutavani. I think somewhere you have did some mistake. Marutavani, please check it properly. You just cancel the calculation and you just leave it. You just close the software and open it from once again. Okay. See here. Okay. So now to do the analysis, once you open your log file, keep the cursor on this file and you just right click and you just go to the results option. Okay. Go to the results. See, there are many options are there. So there are many options are there. Only few options are get activated here, like summary, charge distribution, atom positions, bond properties, surface or contours, molecular group table. Okay, these things are active. So it indicates that by performing the geometry optimization, we can calculate these properties only. Now see the vibration, NMR, UV, ORD. Now these are like not activated. Okay, now these only we can see these parameters. You just first click on the summary option. Once you click on the summary option, you will get this kind of table here. See here. So you will get this table here. So here they have the overall overview of this property. So what kind of file it is, logarithmic file. So what type of calculation you did? You did the optimization. So calculation method, which kind of calculation method we use? We used the B3LYP. So what is the basis set used? All those kind of information here. So what is the overall charge of your system? 0. So what is the spin state? Singlet. Is there any salvation? No, because we done in the gas phase energy. Then what is the energy? So what is the overall energy of your system? So the overall energy of system is minus 155.057984. And it will, whatever the energy calculation you will do in the Gaussian software, it will give the result in the Hartree form. Okay. So, but in the paper, if you see that, they will mention it in the electron volt, right? So you can convert from that Hartree to electron volt. How to convert? So because 1 Hartree is equal to 27.2114 electron volt. So you just multiply this value with 27.2114, then you will get the energy value in terms of electron volt. So usually in the paper, you will get it in terms of like electron volt or in terms of kilocalorie per mole. So if you want to convert this value to kilocalorie per mole, we know that 1 Hartree is equal to 627.5094 kilocalorie per mole. So if you want to convert this whole energy in terms of like kilocalorie per mole, you just multiply this value with 627.5094. Then you will get the energy terms in terms of kilocalorie per mole. I hope it is clear to you. There is a question from like Suhaib. So please show how to save the files. Okay, definitely I will show. First, let me finish this part. After that, I will show it. And then it will give like what is like RMS gradient normal, like normalized function. It is like 0.00066 Hartree per Bohr. Okay, so later I will talk. Okay, later I will talk about this one, but you have to make sure that this value should be like very, very less. Like at least after decimal, there should be like 4 to 5 zeros. Then your optimization was done successfully. So later when I will explain, analyze, do the CHK file, I will explain what exactly this RMS gradient normalization. Now you just consider that this value should be very less, very negligible. Then see here, there is any imaginary frequency. So it won't give any kind of imaginary frequency. So here we want, just by performing the energy optimization, if you're getting any kind of imaginary frequency here, it indicates that your optimization was not done properly. Okay. So there should not be any kind of like imaginary frequency. Imaginary frequency means negative value. So later when we perform this frequency calculation, I will talk about this one, imaginary frequency in detail. So now just make sure that if you're getting any kind of imaginary frequency value, okay. So it indicates that your calculation was not done properly. And from the Rakesh, there is a question, RMS, I got empty. I think somewhere like empty means there is no value, right? Exactly, you got like some empty, or whether it is 0 or empty. If it is like empty, some error is there, you have to done properly. Okay, I think it was not done properly. You have to submit the calculation once again. But here our main focus is the energy value. Okay, more than like RMS, even if it is not showing here, you can calculate the RMS value in other way also. I will show that one also. But here main thing is the energy. We have to focus on the energy. So after that, it will give the dipole moment. See here, by seeing this one, we got that what is the total energy of your system, and we got the what is the dipole moment. So here dipole moment is 1.7768, and we know that dipole moment will represent by using the d by unit, right? So here like it was, and here it will give the what is the point groups, and we know that ethanol is like CS point group. So here it is showing exactly the CS point group. Below that, it will give the like how much time it took for the calculation. See here it is like it took like for me it took around like nearly like 30 seconds for this calculation. Okay, and now if you like click on, now see here the overview, and this is like thermal properties. Now this thermal property is not activated. If you want to analyze this thermal property, so we have to perform the frequency calculation. After frequency calculation, okay, you will get that. So there is a question from IT. I don't know what is your name. It was showing IT here. So what type of energy is it? So it is the overall energy of your system. Okay, total energy. So when I say it is a total energy, it is a combination of all different types of energies which are present, like van der Waals energy, kinetic energy, potential energy, electronic energy. Okay, if you combine all those energy, it will give the overall total energy of your system. Now you may get the question. So here we are getting only the total energy. How to get that? What is the contribution from the kinetic energy? What is the contribution from the potential energy? What is the contribution from the van der Waals forces? If you want to see that, you have to open the logarithmic file. I will show that one also. So there is one question from the VS Gayatri, like what is the reference energy level with respect to which we are getting an estimate of energy value? So what is the reference energy level? So I did not understand what is the reference. Okay. So this one is the we are getting the energy, right? Yes, it is absolute value. So we don't have any reference energy value. Okay. If there is a reference, then you can compare. We don't have any reference. It is a okay. And next, if you click on this optimization, so here you will get all the information. So in optimization, how many steps the optimization process was completed? It was completed like in 4 steps. So what is the maximum force? It is the giving a maximum force. So what is the RMS force? What is the maximum displacement? So what is the RMS displacement value? What is the predicted energy change value? So predicted energy change value means, so the energy difference between the before optimization and after optimization, that is the predicted energy change. But now I'm not going to talk about this term. Okay. So I want to explain this term with proper graph. Okay. With the graphical representation, I will explain after some time. So please wait for that. So from Akshay Kumar, I got this value for RMS gradient. Is there any maximum values here? Let me open that file here. No, nothing. I think in your case, it was showing it in terms of like atomic unit. Okay. So here the values are showing it in terms of like atomic units. Okay. In my case, it is in Hatry. You just change the, because I think in overall, you just go to the overall preferences. There you need to change the what is the unit. There also you can change. You can just fix the electron volt or kilocalorie per mole. In your case, it was showing in atomic unit. That is the only difference. And so from Chandra Prakash, like, sir, opt inactive. Opt inactive means in your case, the calculation was not done properly. Okay. Somewhere you did some mistake. Please check it. And from Suruchi Chinia, there is a question, can we calculate for the doped sample? Yes, we can calculate. Okay, you can calculate it, but it will take more time. But here I can't show. So any other questions, if you just write it in the chat box. Okay. And now if you want to save this file, you can just see here. If you want to save this data, even this report also, if you want to save, you just click on this file down arrow button. And if you just click on the save data, so you can save this entire data here. Okay. Let me just click on the OK button. And now from Sachin Kumar, okay. Yes, there is nothing wrong. You are getting proper only. Okay. No need to worry about that. So in your case, it took like 97 steps to not converge. Yes, in your case, see, the optimization was not done properly. It was showing that like not converge because the difference is very not that much good. So in your case, the calculation was not done properly. You have to perform once again. And if I see it here in my case, let me close this one. Open this, right click, go to the results here and go to the summary. See here, all are like converge. So the calculation was done properly. Okay. So if it is like not converge, calculation was not done properly, how to do it once again. Okay. I will explain this part later. I hope it is clear to you. Okay. So now how to calculate these Mulliken charges, partial charges, all those kind of things. To that, again, you just right click, go to the results option. Now, instead of going to the summary, now just click on the charge distribution. Okay, just click on the charge distribution. So once you click on the charge distribution, so this window will pop up here. Okay, so now here in type of like atomic charges, the type will be there. There are like many type, like different type like ASP, NBO, different types. And now we are going to calculate the Mulliken charges. Okay, so if you click on this molecular charges here, there is one, let me open it here. Yeah, this, okay, I think this is not good. So did you took same ethanol molecule? See the point group, because the ethanol point group is CS, it is not correct. Dipole moment is okay. So which molecule you took? Yeah, depending on that, the values are changed. So if you took the different molecules, then don't compare energy values and RMS gradient value with my molecule. Okay, whatever the molecule you have taken, it will depends on what kind of molecule you have taken. And what the main thing is, along with the energy, you have to go to the optimization option. If it was showing that not converged, then you have to, the calculation is not good. You have to do it once again. Then it point group may be fine. Okay, if the molecule is different, then it may be different. Okay, it's no problem. Then you have to check that. So Amalendu, okay, in my case, optimization is not activated. I think the calculation was not done properly. You have to repeat it once again. If it is inactive, then you have to do it once again. Okay, now let's come back to this option. You just click on this molecular charge option. And now here, you just click on this, activate this number, show number. Once you click on this show number, see, it will give the charge. So the charge on your like carbon, his first carbon is 0.431. This carbon is like 0.081. And this oxygen is 0.535. And we know that, right? Among these all molecules, which is a more electronegative, oxygen, definitely oxygen should have like more energy, like charge. So all the charges and even know that so oxygen is negatively charged, then electronegative. If you compare the electronegativity of like oxygen, carbon, hydrogen, that is a basic thing. But if you're from physics background, so oxygen is more electronegative compared to carbon, followed by hydrogen. And it was showing exactly, see, it has more negative value. Then these are the carbon negative values. See, and if you compare this one, so this carbon has more negative charge compared to, more electronegative compared to this one. Why? So because this carbon is connected to the highly electronegative oxygen. So because of that, see, if you change, you may get the question, because both are carbon, why they have the different charges? Because this, we have to see the neighboring atom also. So it is connected to the this highly electronegative oxygen. Because of that, it charged like it is more electronegative compared to this carbon. And this, all the hydrogens are like, you can see the charges here, like, okay. So like that, you can calculate the molecular charges of each atoms which are present in your molecule. And if you want to color them atoms by charges, if you click here, so it will color the atoms by charges. Okay. So depending on the charges, it will see, it will give the coloring. And here, you can just symmetric color range, you can give the symmetric color range also. And if you want a fixed color range, you can give the fixed color range also. Okay, like that you can visualize. And even like here, like if you want to show the vectors also, you can just activate this button. So it will give like what is the direction of your vector, dipole moment. So what is the dipole moment direction? See? Okay. So there is a question from the Bhargav. For me, only Mullican enabled, remaining not enabled. Yeah, because we did only, see, for me also only Mullican is enabled. Remaining like everything is inactive. So because for optimization, you will get only Mullican charges. But if you want these information, it will, we have to open the different files. Okay. In my case also, I think you are not seeing the screen here. Okay. No need to worry much. You just see like what exactly, because for optimization, it will give only the Mullican charges. And here, it will give the, what is the magnitude? Magnitude is nothing but your dipole moment. And again, it will give the direction. What is the direction of your dipole moment here? And if you want to increase the scale, see here, you can increase the scale also by using this one. And from origin also, you can just change the, here, like a default charges, origin charges here, you can just like from the center of the mass, it will go here. And you can choose from the like center of the nuclear charge. You can choose, it will change the position here. Let me, electronic charge, it is like a nuclear charge, and it is from the center of the mass. I will suggest you to go with the center of the mass. And if you want to save the structure, you can just save it here. Once it is done, same procedure. Okay, previously some of the participants, they asked how to save. If you want to show this one, okay, just right click here. Otherwise, you just click on this button, save button, and you just save it in the TIFF format or like PNG format or whatever the format you want. Okay, I don't want to save it. I will just close this one button. Okay, so now I hope it is clear to you how to calculate the Mulliken charges or dipole moment or vector. So far, we got the information about the total energy of the system. What is the dipole moment? What is the point group? Then what is the Mulliken charges? What is the direction of the vector? Right? I hope we got all those kind of things. So do you have any questions so far? So from Amal Shashi, there is a question. Can you tell once again how to open the charge distribution? Okay, I will show it. And from Bhargav, I checked the screen but could not figure out whether those are enabled or not. Okay, Bhargav, no problem. Okay, so now what I will do here, Amal is asking me to repeat it. Okay, okay, cancel it. It will go here. So once you open your log file to show the charges, right click and go to the results, then go to the charge distribution. Okay, it will give. And here, if you click on the type, it will only activate like Mulliken charges. Now you just select only this one. You can just click on the show number. If you deselect like show numbers. So the charge range is varying from like minus 0.5 to plus 0.5. So here you can see that the negative, the red color indicates that negative charge, darker green indicates that positive charge, in between like that. It will go with like this kind of colors. So these are color scale. So let me cancel it. I hope it is clear to you. So do you have any other questions, please? If you have any questions, please write it in the chat box, or if you have facing any kind of technical issues. So if there are no questions, if it is everything is clear, then type Y in the chat box. So then we'll go to the next part. Okay. So now let's try to get how to create this optimization plot, because we have done the optimization, right? So we have to show it in a graphical format, like how the optimization was done. So what is the energy before optimization? What is the energy after optimization? So how many steps it took for the optimization? So what is the energy change in each step? How to represent it in the graphical way? Okay. So before that, I'll just close this one. Okay. So before that, like some of the participant asked that what type of energy? I told the total energy. And if you want to see the overall energy in that case, see here, it will create some logarithmic file here. Let me check here. Opt. I think this is the logarithmic file. Let me check the properties. Yes. So this is the logarithmic file. You just open this file in the notepad. Open this file in the notepad. If you yeah, this is like your file. And if you scroll down here, you will get all the information here. Energy, see different kinds of parameters, coordinates, how the things happens, everything. You will get all the information here. And let me some point, if you need to find out what is the total energy. So Mulliken charges, everything here. Let me control F and give me the like energy. I will just give the energy. Hit the enter button. So it will, now I will just see here the nuclear repulsion energy, how much. So if you click here, it will give you there are total rotation. Scroll down, let me click on the next button. Total kinetic energy from the orbitals. You can nuclear energy, kinetic energy. Then here the predicted charge in the energy. So this is a charge. And if you click here, you will get the different types of energies also. Here like requested convergence on energy. Okay. So nuclear repulsion energy. At the end, it will give one paragraph. There it will mention all type of energies. You have to find out where exactly it is. The kinetic energy. Okay. Here it is showing like kinetic energy and nuclear energy. Yeah. So here you will get all the kind of information like different forces, even like these are like forces. So what is the force on each? See, this is like your atomic number of each atoms. So, and how the forces on each atom, like along the X, Y, Z coordinates, how the forces are there. Nuclear repulsion energy, because it will change the energy value after each iteration, because it took 4 steps, right? Like a 4 iteration. So each iteration, these values will changes, and you have to consider the last iteration, whatever the iteration it was took. From there, you have to consider. You can just check your all file it here. Okay, and you can from there you can get all the information. So here, see, and if you see, focus on this paragraph. So this is the total kinetic energy from the orbitals. And there, if you come here, it will give the Hartree-Fock energy value. See, this is the Hartree-Fock energy value. This is the main energy. The total energy of this is the main energy. Hartree-Fock minus 155.05. And what is the root mean square deviation? So deviation energy value, what is the root mean square fluctuation energy value? So what is the this quadrupole, dipole values are there. And here you will get a lot of information here, okay, for each atoms, all those kind of things. The logarithmic file, you can do the analysis also. Let me close this one and now come back to the software. Okay. Okay, so now to plot the optimization curve, so we are going to use the log file once again, but there is one trick. Whenever you are going to plot this optimization plot, so while opening your logarithmic file, so there you have to activate some files, like some coordinates. Let me show how to do that one. Okay. Now you need to open your log file. You just go to the file menu, then click on the open. Then you just go to the folder where your files, like output files, are present. In my case, it was present in the desktop. So directly it is opening the desktop. And now we are going to open the logarithmic file, right? This one, ethanol underscore opt log file. You just select the log file and you just click on the open. Okay. So now if you open like this, here you can't plot any kind of optimization plot. Okay. So you should not open like this. Okay. I'm going to show it once again. If you want to plot the graph, go to the file menu, click on the open and select your logarithmic file. Okay. Once you have selected your logarithmic file, here, if you come at the bottom, like left corner, bottom corner, there is an option. Read intermediate geometries, like optimization. Okay. So whenever you are going to plot the graph, you have to activate this key. You just check this box. Read intermediate geometries. In bracket, it was mentioned that optimizations. Okay. So once you have selected this key and you just click on the open button. So now we can plot the graph. See, now there is like different things are there. If you click here, see. So this is the, after first iteration, this is the structure. So these are like after second one, after third one, after the fourth step of iteration. You can just see here and you can change like different kind of, see, it is like your first one, second one, third one. See how there is a slight changes, right? So this is the first one. After first step, if I go with the second one, there is a slight change in the structure. See, now there is a little bit decrease the bond length, like how the steps are going on. You can just visualize here. Okay, let me minimize this one. Okay. So now here, what you need to do here. Now just right click, then go to the results. Now here you just, now the optimization it got activated. So if you open the directly without checking that optimization coordinate geometries, you won't get this option. If you want to activate this button, you have to open like this, whatever the procedure you have followed. So now to plot the graph, you just click on this optimization button. Once you click on the optimization button, see, you will get the, I hope it is clear to you. So this is your, let me show the plot. And if you click on the plot option here at the top left corner, there are many options are there. There are different plots like total energy, RMS gradient, normalization, maximum internal force, RMS. If you want to show all the graphs, you can activate. Otherwise, if I want to show only one, I'll just deselect everything. Then it will give only the, I want to like total energy. So this graph represents how the total energy of the system, your molecule, is changing over different iteration. So along the x-axis, it was representing the optimized step, number of steps it took for the optimization. Along the y-axis, it is giving the total energy in terms of like Hartree. So this is the energy of your system before optimization. It is like minus 155.055 hat rate. And after first iteration, so the energy will came to here. And the energy is like nearly like 155.058, near to this value, not exactly near to this one, right? Even like if you compare this one, you won't find much difference in the hat rate. But if you convert to energy in terms of like electron volt or kilocalorie per mole, there is a much difference in the energy value. And this is the energy change after the third iteration. Okay. And this is the energy change after the fourth iteration. There is no difference. See, there is a straight line. As there is a no difference, the software will detect that the optimization was done successfully. So that is the meaning of that. I hope it is clear to you. So like that, you can plot the graph here. And you can save it this graph also. There is one question. Let me see. Marutha Vani like uploaded some screen here. Yeah, I think you did not activated that key. You are opening like you are not following the step. I think that is a mistake you are doing, Marutavani. Let me explain that one. Even Mazida is asking to repeat the plot. Okay, so what I will do it here. So this is the last time. Just listen it carefully. So if you want to plot the graph, so to open this thing, what you need to do, you just go to the file menu and click on the like open. Then select your logarithmic file. Once you have selected in this folder only, don't click directly on the open option button. So if you come at the bottom left corner, there is an option like read intermediate geometries in bracket, you have the optimizations. Okay. So previously it was like this. It was like not selected. You have to check this box. Okay. If you check this box, then only that optimization button will be activated. And now you just click on the open. And now this is your structure now. So to open that, you just keep your cursor on this, whatever the logarithmic file is there, right click, then go to the results, then go to the optimization. Okay. Now you can just analyze your results here. So this is the optimization plot. Like, and if you want to save this graph, how to do that? Here you can just right click here and you can just click on the save data. Otherwise, you can go here also. Otherwise, you just keep your cursor on the graph, right click. There are different options. Okay. So like there is like instead of doing like individually one by one, you just right click. You can just hide other plots. Then it will show only this plot respectively. And then like if you want to print this one, you just click on the print. And if you want to save the data, like only data, and you can, if you want to plot this graph by using your MX Excel or Origin software, then you can save the data only. So it will save the data in the text format, and you can plot the graph. You can beautify it by using the other tools also, graphing tools also. Otherwise, if you want to save this graph as itself, just right click and click on the save picture, and it will save this one. And you just give the location where you want to save that one. File location, okay, it will be in the desktop, and it will be in the, like you can save it in the different like SVG format, PNG format, BMP, PP format is there. So let me save it in the PNG format. Okay, and once you have done, and you just click on this save button. Once you click on the save button, it will be saved here. Let me check it here. Yeah, this one. Now you can open it. So this is a graph, and you can use it for your publication. Otherwise, if you want to still show it in a different way, you can just save the data in the text format, and you can just plot the graph by using Origin or M.Sc. Right click, results, optimization. I hope it is clear to you. Okay. So here, once you have saved this plot, there are like other plots also there. Even if you want to know exactly, see here, the optimization step number 3. Like if you can select, see here, it is here, the after energy. But if you want to find what is the exact energy here, you just select this one. You just select here. At the bottom, it will give. So what is the optimization step number 2? So what is the total energy of this step? Like minus 155.0579. And if you want to find energy of this one exactly, just select this point. It will give the information here. And even if you select it here, so like that, how you are going to analyze it is very important. Okay. So even like that, even I have shown that only the Mulliken charges, right? Even previously I have calculated the Mulliken charges. Okay. And just by, you should not remember, like note down only the number and image. From there, you can explain, you can connect to your application also. For example, let's consider So what is the Mulliken charges? So Mulliken charges are nothing but it is like distribution of your electronic charge within your molecule, right? Okay. So like it will be calculated on like each atoms which are present in your system. So some are like positively charged or some are negatively charged. So what is the meaning of that? So what if it is like positively charged? What if it is like negatively charged? If it is like negatively charged, it indicates that they are nucleophilic in nature, right? They are nucleophilic in nature. If it is like positively charged, they are like electrophilic in nature. If they are nucleophilic, electrophilic, then you can compare with your reaction mechanism. Okay. So if it is like nucleophilic, how exactly it will react? If it is electrophilic, what kind of reaction it will undergo? So you can connect like that. By those numbers, how you are going to connect, it is very important. Now, okay, there are other graphs are there. Okay, already it is 11:30. Okay, can I extend it for another 15 minutes? If you're okay with that, I will extend. Otherwise, we'll continue tomorrow. So because it is up to you. So because I want to explain everything in detail so you can understand it. Please respond. So can I continue or what? Okay. So there is a question from Akshay Kumar. Red is nucleophilic and blue is electrolyte, sir. So where is blue? No, here like here red one is like not nucleophile. That is like oxygen. Okay. So that is oxygen atom usually will represent in the red color. You have to focus on the charge, whether it is negatively charged or positively charged. So negatively charged are like nucleophilic and like positively charged are like electrophilic in nature. In Gaussian software, by default, it will give for like negative charges, it will be indicating the red charge and positively charged atoms will be like represented in terms of like green color. So your molecule is showing blue and red. Okay. Can you just upload the screenshots? Then I can get to know what exactly it is. Okay. So now other than that, there are some other graphs are there. Right click. Let me click on the show all plots. And if you come down here, see there is RMS gradient. So previously in that summary, so it was given the what is the RMS gradient value, normalization value, what is like maximum like internal force value. So now here you will get the graph here for all different, you will get the graph here. The first one is the RMS gradient norm. Okay, so here also along the x-axis you have the number of optimization step. Here you will get the RMS gradient norm, like root mean square gradient energy value in terms of Hartree per Bohr, and like how these values are changing after like each iteration. It will give the information. So what exactly this RMS? So it is a measure like some of the quantity. It is used to assess the convergence of geometry optimization, like whether the convergence was done properly or not. Okay, so it indicates that how close the current geometry of your molecular system is to the stationary point. So stationary point is nothing but the minimum point, or you can call it as a saddle point. Okay. So Akshay Kumar, let me open your image. Okay. So see, you have taken the different molecule. That's why when you are going to do hands-on, it will be good if you take the same structure. Okay, fine. Even if you have taken the different. So here, blue means it is not like electrophilic or not like electrolyte. It is like that nitrogen. So whatever the molecule you have taken, it is the like a heterocyclic compound. So usually when you draw the molecule, this gray color indicates that the carbon atom. Okay, this white one, small one indicates the hydrogen. The red one indicates the oxygen. The blue one indicates the nitrogen atom. I hope it is clear to you, Akshay Kumar. Okay, perfect. Just let me close this one. Okay. And now here the question will come. So how to measure that whether the convergence was done properly or not? So I told that, so it indicates by using this one, we can find out, so whether the convergence was done properly or not. So how to check that whether the convergence was done properly or not? So here, let's consider if you are getting the low RMS gradient value. If you are getting like low RMS gradient norm value, it indicates that the geometry optimization has converged to the stationary point. So here, which is the stationary point? The zero line. See, if you see the graph here, it was exactly connected to the 0 point. If you click it here, it will show the value here. What is the exact value? It is like 6.6135 into 10 to the power of -5. means 0.000005. It is almost 0. Okay. So that is the meaning. You need to get, if you are, how to find that if this value is almost equal to 0, near to 0, it indicates that the convergence, the geometry optimization was done properly. Okay. So that is the meaning of that. If the higher value suggests that, the higher value of RMS gradient norm suggests that the optimization process not done properly, it may need further iteration to achieve the convergence. That is the meaning of that. Okay, that's why these values are very important. You will get only the numbers, but if you go deeper into that, it will give a lot of information. Okay, so when we can consider the structure was properly optimized, so this RMS gradient value should reach the saddle point. Okay, the minimum point or stationary point of your energy. That is the meaning of this RMS, and you can save it in the similar way. And if you scroll down, there is one more graph, is there, like maximum internal force graph. So what is the maximum internal force graph? Okay, so here the maximum internal force refers the highest magnitude of the force acting on the atom within your molecular structure during the optimization process. See, like that, in your atom, there are many, in your structure, there are many atoms are there, right? It depends on that. What is the force acting on each atom? There is some amount of force acting on each atom which are present in your molecule. Okay. But in this curve, it will give the overall force. Okay. It won't give the individual atom force. In the graph, it will give the overall. But if you want to find out that what is the force acting on the individual atom, in that case, you have to open the logarithmic file in the notepad. There you will get the table. So from there, you can find out what is the force acting on each atom. You can find out it here. Okay. So when the maximum force of your molecule approaches to the 0, so it indicates that the force on all the atoms have the balanced. Okay. So which suggests that the stable geometry has been found. That is the meaning of that. So before optimization, there is some amount of force acting on each atom. But after optimization, so whatever the forces which are acting on each atom, either it may be the positive force or negative force, after the optimization, it should be 0 or it is near to 0. So then it can your structure reached the stable configuration. If you scroll down here, like maximum internal force, see here. So this is the before optimization, the force on the overall force on your system is like 0.02. And after optimization achieved, here like it is like 0.000139. So where is 0.02 and where is like 0.000139? It is almost very negligible, and you can consider it as a 0. So the higher value of maximum internal force indicates that the geometry of your molecule is not optimized properly. Whereas the smaller value of your maximum internal force indicates that the convergence and optimization was done properly. Okay. Because what people will do, just they will submit the job, and they will get some energy value, and they will tell that, yeah, optimization was done, and they will put it in the paper. But that is not the proper way. So you have to check all this property. Okay. So you have to check how the energy is changing, how the RMS gradient normalization is changing, how the maximum internal force is changing. So then only you will get the proper details. Okay. There is one question from Sachin Kumar. This graph shows only one molecule. Then how can I represent series of molecules in one graph? So series of molecules means, I did not understand. In series of molecules means, like here we did only one molecule optimization, right? Then for it is giving for the only one molecule. And if you want to represent it for the series of molecules, let's consider you have the 10 molecules. And if you want to compare of all the 10 molecules, in that case, what you need to do, you need to perform the energy optimization for all the 10 molecules individually. Okay. And then you have to save data, like right click and save the data in terms of like test format for all the 10 molecules. And then plot the graph either by using the Origin software or by using the MX Excel in one graph. Okay. Then you will get all the one graph. I hope it is clear to you, Sachin Kumar. Okay. Now let's go to the next graph, that is maximum internal displacement. See, first we have talked about this gradient value, RMS gradient value. Then we have talked about the force value. Now we are going to focus on the displacement value. right? So there is like two forces are there. One is like the maximum internal force. Next one is the RMS internal force. Okay. So what is the difference between this maximum internal force and RMS internal force? Okay. So here the RMS internal force provides the information that the average magnitude of the force acting on the atom within the your molecular system during the geometry optimization process. Okay. So it is like average force, whereas this RMS internal is the average force. This is the maximum force. Okay. I hope it is clear to you. So maximum means overall maximum force. Average means if you take the average of all the atoms, then how much it is. That is the difference between these two forces. So here also, lower the RMS force indicates that the geometry is closer to the convergence, and it represents that like more accurate prediction of your molecular system. So whereas the higher value of RMS force suggests that additional optimization steps may be needed to achieve the stable geometry of your system. So that is the difference between the RMS internal force and maximum internal force. I hope it is clear to you. The next one is the maximum internal displacement. Now we are going to talk about the displacement. Okay. So here the maximum internal displacement refers to the largest movement or displacement of any atom within the molecular structure during the geometry optimization process. See how, like for example, this is a position. Like let me see here. I will just change this one. Let me enlarge this one. If you focus here, if you change the coordinates, see here like number iteration. See now there is a little bit movement here. See now there is a displacement because from here to here it was shifting its position. Okay, so that is known as the displacement. So this maximum internal displacement graph indicates that. So how the change the displacement of atom is taking place in your molecular system during the optimization process. So the large maximum displacement indicates that the molecular structure is still can form its like optimized configuration. So whereas like small value of maximum displacement suggests that the structure is likely converged to a stable configuration. It is very simple. Like you can just sit here maximum. So previously it was this much of displacement. Now see here the displacement is very less. It was attained here. In all the cases the value should be low. That indicates that the optimization was done properly. And similarly, like RMS internal displacement, like similarly how we have like a maximum internal force and RMS internal force. Similarly, we have the maximum internal displacement and RMS internal displacement is the overall maximum internal displacement. And this is the average internal displacement. Similar thing. Okay. How the average displacement, like overall, if you consider and if you take the average of all the atoms, how much it is. And here also the value should be less. Okay, so like that you can use this graph and you can use it for the publication and you can just explain all the things. So these things are very, very important. So as a researcher, this is how you need to interpret by using those numbers by the graphs, and you can apply them like you apply them to your application. What kind of application you are doing, according to that you have to connect them. How these values are can supplement your experimental data. I hope it is clear to you. So do you have any questions so far? If you have any questions, please write it in the chat box. If there are no questions, if everything is clear, then just type Y in the chat box. So I have to respond fastly, so then I can go to the next topic. Okay. Okay, now let me show how to plot the electron density diagram. Okay. So let me close this one. Let me everything close. Let me open this one. Schedule. Yeah. So far what we have done these things. We are done with the demonstration and we have done with the output. What is our next step? Calculation and analysis of electron density surface. So I will cover, at least I will finish this two part today. Okay. So at least we can start from today. So because this will take, if you understand these thing parameters properly, here we can go a little bit faster. So now I will finish these two part. Within like 10 minutes, I will finish these two things. Let me come back to the software here. Okay. So how to plot the electron density diagram. So later I will explain what is exactly the electron density diagram, then how to get the information from that. First, let me show how to open this electron density. So if you want to plot this electron density diagram, and if you want to plot this molecular electrostatic potential, for that we have to use the CHK file. Okay. So whenever it will comes to the just numerical data and graph, there we have to use the logarithmic file. Wherever it comes to the figures, okay, like surface, all those kind of things, and then we have to use the CHK file, that is checkpoint file. So how to open that? Very simple. You just go to the file menu, then go to the open. Then here you can choose the CHK file, ethanol underscore op.chk file, checkpoint file. Select this one. Okay. And you just click on the open button. Okay. Click on the open button. So once you click on the open button, see it will open the CHK file, checkpoint file now here. And now to get this electron density diagram, click on the right click, go to the results. Okay. So now here you just click on this one. Okay. Surface or contours. You just click on the surface or contours. So once you click on the surface or contours, you will get this window. This window will pop up here. Okay. So here what you need to do is just click on the cube action. So click on the cube action and you have to choose the new cube. Click on the new cube here. So once you click on the new cube, you will get one more window here pop up here. Now what you are going to calculate, you can choose it here. The type is there here. You just click on this drop down menu button. So now here you can see, you can represent the molecular orbital. You can represent the total density, or you can represent the alpha density, or you can represent the ESP electrostatic potential, or you can represent the Laplacian values, density, Laplacian density. But what we are going to show now, we are going to show the total density, right? You just select the total density here. Okay. Select the total density here and just click on the OK button. Click on the OK button. So once you click on the OK button, it will close. Now you just click on the surface action here. Okay. So click on the surface action. And here you just click on the new surface. And now see. So this is the electron density over your molecule. But it was not looking, everything is covered, right? So now you can represent it in different color. So to represent it in different color, so very simple, you just click on the right click, then go to view, then go to the display formats. Now you just come back to the surface. Now instead of solid format, you can consider the mesh format. See, now you can represent in the mesh format. I think in the papers you have seen this kind of diagrams. You can visualize how the electron density, otherwise like transparent, you can choose this one also. And like transparency, you can just represent how transparent you want. You can just change it here. So like if you want to represent only the positive density or negative density, you can choose it here like positive only, or you can just so negative only, otherwise just click on the both. Both is the best option. And you can save this image like similar way, whatever how you followed for your previous one. And see, there are different color, like this greener part is there, like pinkish part is there here. Let me change the background to the black one. Black one, so let me keep it like white. Yeah, here you can identify some kind of color changes, green, pink, a little bit here. And here also you can quality, you can do whatever the things you want here. Okay, so now let's try to understand what is electron density diagram. Okay, so your electron density diagram is the graphical representation of the overall distribution of electron density within your molecular system. How the electron density is distributed throughout your molecular system. So this diagram is very important for understanding the various chemical properties or behavior of your molecular system. So usually it will represent in different colors. Now see, there are some colors are mixed here. Green, pink, a little bit of whitish color, all those kind of things is there. So I can call it like cyan color, all those kind of things. So now the question will come here, like the different color represents the different level of electron density. So usually it is like represented in red, orange, yellow, green, cyan, different colors are there. Usually the red color indicates that the very high electron density. So if there is orange color, if it indicates that high electron density. If there is a yellow color, it indicates that moderately high electron density. If there is a like green color, it indicates that the medium electron density. If there is like cyan color, it indicates that like moderately low electron density. Okay, if there is like blue color, it indicates that low electron density. If there is like dark blue or purple color, it indicates that very low electron density. So that is the meaning of that. So with the help of electron density diagram, you can explain the chemical reactivity of your molecule system, how whether it is chemically reactive or non-reactive. How? Usually the region with like high electron density are nucleophilic in nature. So nucleophilic sites means they are electron rich sites. So whereas the region with low electron density are electrophilic sites. They're like electron poor site. So that is how you can extract the data and you can compare with whether it is like reactivity high or less. You can do that one also. Even like there is a cube action, you can click on the new cube here. You can just other properties also, total density, and if you want like molecular orbital, like other ESP, electrostatic potential diagram, if you want to represent in later I will show it here. And like alpha density is there. You can click alpha density, open, and you can just click on surface here, new surface, electron density, yeah, total alpha density, select here, new surface. Then it will give the alpha density, alpha ICFC, both. Now let me showing hide surface. Hide surface. See, this is the alpha density. Now this one, what is the showing it is? It is the alpha density. So like that, you can visualize the different types of density through your system. So let me close it here. Now let me show how to plot this. Other than that, okay, I'll just close this one. And even there is like some band properties you can calculate. Let me show it here. Let go be open. You can open your log file. You can just click on the open button, right click, go to the results. Then if you see here, see atomic properties, you will get here. If you want to get the atomic property, right click, go to the atomic property, and you can see it. You can see the atomic number, what is the mass, what is the molecular charges, forces on the nucleus. Let's see atomic number. You just click on the show numbers. It will give the atomic number of everything. And if you want to check the mass, you can select it here. It will give the atomic mass of each atom after optimization. Okay. And if you want to see this molecular charges, it will give the molecular charges here. And if you want to give this like force on nucleus, see, this is very important. After optimization, the force should be 0. If it is like there is some amount of force, it indicates that optimization was not done properly. See, the forces on the nucleus, it is 0. This is very, very important. You can visualize these various properties. Similarly, like right click, go to the results. Similarly, go to the bond properties here. And from bond properties, see, you can find out the length, bond order, everything, bond length, show numbers. See, so the bond length between this one, OH bond is 0.965. So this like CO bond is like 1.432. Okay, see, it is in terms of angstrom. So this is the bond length. Like you can find out the bond length of each bond which are present in your system. Similarly, if you want to find out the bond order, you just select here, see, each bond order it will give. See how many properties like you are calculating just by performing the optimization of your structure. Okay, so let me close it here. Similarly, right click. You can calculate everything by using the logarithmic file. Go to the results and the surface contour, it won't show these two. And let me show, now I am going to show you how to plot this electrostatic potential diagram. Okay, later I will explain what is electrostatic. Let me open. So to plot the electrostatic diagram, you need to open your CHK file, checkpoint file. So for that, you just click on the file menu, then go to open, then go to desktop where your file is present, open the CHK file. Okay, then click on the open button. Same procedure, how you plotted this electron density diagram, you have to follow the same procedure. Once you open your CHK file, right click, okay, and then go to the results, then go to the surface and contours, and here you just click on the new action, cube action, and click on the new cube, and here you have to choose. Previously, you have selected the total density. Now, if you want to visualize this electrostatic potential diagram, you just select ESP electrostatic potential. Okay. And then you just click on the OK button. So once you click on the OK button, yeah, it will update it here. Once it update here, once you will get this information here, so this button will be activated. Surface action, you just click on the surface action now, and you just click on the new surface. So now it will give the electrostatic potential diagram. See how you can visualize how the electrostatic potential diagram is there. And after that, here also you can just represent, you just go to the cube action, right click, view, and you just go to the display format here, and you can just change its surface in different format like mesh. Okay, and you can just represent, and you can save it, and you can put it in your publication here. Okay, now let's try to understand, once you plot this graph, like how to get the extract the information from your ESP diagram. So first understand what is ESP diagram. Okay, so this electrostatic potential diagram is also a kind of like graphical representation of your the electrostatic potential created by the electron density and the nuclear charges of your molecular system. So these diagrams help us to visualize like how the molecule might interact with charged species and provide the insight about like its reactivity or like intermolecular interactions, all those kind of things. So as like how this electron density diagram is color coded, this ESP diagram also color coded. Usually it will represent with different kinds of color, like the region shows in the color like blue or purple indicates some kind of like positive ESP, like electron deficient region. So whether like regions with colors like red or yellow, okay, indicates that negative ESP. Like those are like negative ESP means electron rich regions. So with the help of like this electrostatic potential diagram, you can predict how the reactivity of your molecule changes, like whether it is like chemically reactive or non-reactive, all those kind of things. Usually this region with like negative potentials, they are like acts as a nucleophiles, means it can easily donate the electron. So whereas the region with like a positive potential are like likely act as a like electrophiles, and can easily accept the electrons. Okay, so with the help of your like ESP diagram, you can also predict the hydrogen bond donors or acceptor site in your system. Usually the region with like positive potential can form the hydrogen bond with the region with your negatively potential region. Like negatively potential means like lone pair on your oxygen or nitrogen atoms, whereas like positive potential means like hydrogen atom attached to the electronegative atoms. So like that, you can extract a lot of information. Even based on this interaction, okay, once you know this interaction, so you can predict like how it will interact with the solvent by using this ESP diagram. Okay, you can just predict how like effect of solvent, how this interaction molecule with the solvent molecule. So usually like polar solvent will interact with the more strongly with the region with positive or high negative potential, polar solvent. Okay, we know that in the solvent there's a polar, non-polar solvents are there. Usually these polar solvents will interact with more strongly with the regions having the high positive or negative potential. So like that, you can extract a lot of information from these diagrams and you can connect with you. Okay. So there is a question like how to save this diagram. Very simple, like right click here, you just go to the, otherwise here, close here, and you just go to this, let me close this one. Just go click on this option and you can just click it here, save this one. Okay. Otherwise here also just right click and then here go to the file option. From here also you can just save it, or you can save it as an image also. You can go it here. There are many options are there, you can use it. So how to find the ESP region? So ESP region means it will create this kind of surface based on the color coding. You have to find out that I told the color coding like yellowish, reddish. If it is like positive, you will get a kind of like a negative, like red, yellowish. Depending on that one, you will get. If you want the exact amount of value, how the electrostatic potential value and the each atom, in that case, you have to open the logarithmic file in the notepad. So in that it will be table will be there. From that table, you can get out what is the exact ESP value on each individual atom. So when it comes to this kind of structure, we'll focus overall electrostatic potential instead of individual atom. So here also you can just represent it. Let me close this one. There is, even you can change this color region also. Let me right click, results, go to the surface and contours here. Even like you can map it with the total density. Okay. So now here you can just change the color. See, now you can change the color also. Now green, blue. If you want the color scale, automatically see the red one is like negative. The blue one is the more positive one. In between, there are many color. Red is there, yellow, green, the sky blue, dark blue. Okay. Like that, you can easily find out it here. So which region is acting as like electropositive and which is like electronegative. So here also you can just, again, you can just go to the right click, go to the view option here. Yeah, display format here. You can just go to the mesh format. Or you can go to the transparency also. Okay, and mesh here also you can go choose which one, like both positive only. See here. So this is the positive one. And if you want like a negative one, you can just choose the negative one. Change here. If you want to show both, you can just click here both. Two layers. One is positive, one is like negative. I hope it is clear to you. Okay. So now let me close this one. And like Akshay Kumar is asking, can you please tell it, sir? Which one? Like electrostatic potential value of each atom, like by using the logarithmic file. So I have to mention it clearly. Okay. So we are already late by 30 minutes. So I will stop it here. Okay. So this will complete the optimization of your geometry. So you have to follow the same procedure, whatever type of material it is. Either it may be like organic, inorganic, 2D materials. You have to follow the same procedure. So tomorrow we are going to do other like spectral characterization, how to perform this frequency calculation like Raman IR, like NMR spectra, Raman activity spectra, VCD spectra. So tomorrow we are going to do all those kind of things like UV, all those kind of things. We'll do it tomorrow. So this is the main. Today's session is very, very important because in the today's session, I have explained a lot of things. So those are very useful. And you have to use the same type of parameters for all other type of calculation. From tomorrow, I will go a little bit faster. So because we are already done with the 2 days, we are left with only another 3 days. But still we have completed the day one portion, right? So I have to cover all those kind of things. But no need to worry. So whatever we have mentioned in the flyer, I am 100% sure I will cover everything. You don't need to worry about that. So if you have any questions, please write it in the chat box. Let me close this one now, window. Let me open this logarithmic file. You just open your logarithmic file and you just type, I think, Control F. Electrostatic potential. We have to. Otherwise, let me type potential. We have to find out what they have term they have given. It is not there. Let me, you just select it here and you have to scroll one by one. You just slowly come down and you have to find out that where is that electrostatic potential values are there. Akshay Kumar is asked like how to find the values here. These are like eigenvalues, orbital configuration. So density matrix. You just scroll down slowly and you have to find out here. So Mulliken, see like there also we have the Mulliken charges. So here also in the list, they have given like what is the Mulliken charges on each atom. And here they have given like all electronic contribution there. And see here also you'll get like orbital population, how these electrons are population, like different orbitals, 2s orbital, 2p orbital, what is their contribution in each orbital, you will get the information. From the log file, you will get a lot of information. So there is a question from like Akshay. So as you said, like ESP region must show like red, blue. What is if the molecule shows only red? If only red means it is like highly electronegative region. That is the indication. That's it. Depending on the color. So it don't has any kind of like electropositive region. It all the regions are like electronegative in nature. Okay. So like that you have to consider. So there is a question from Ankita. While studying the interaction between the two molecules, should we optimize the geometries of individual component first? Yes. In that case, what we need to do, we have to optimize the individual atom first. Okay, so then you have to check that what is the energy of like consider you have two atoms like A and B. Okay, and you have to study the interaction between A and B. So first what you need to do, you have to optimize A separately, optimize B separately. Then you have to make the composite of A and B. Then you have to optimize separately. Then you have to compare that. So what is the energy charges when alone A alone? What is the properties of B alone? And what is the properties of the composite, both A and B? Like that you have to compare. I hope it is clear to you, Ankita. There is one question from Rakesh. So when I open log file, I am not getting green iteration option. Green iteration option means I think you are not opening properly. You just go through the recordings, Rakesh. So if you want to get this green iteration operation, you have to open the, see, whenever you open the logarithmic file, you won't get this green iteration option. If you want to get this green iteration option, you need to open the CHK file. Okay. So while studying the interaction of A and B, we will be considering the different option. Yeah, that is also very important point. Yeah, actually, so whenever we'll go study the interaction, we'll consider like different view, like top view. Okay, then like we'll kind of like side view, like kind of like bridge view, then like halo view. So how it will interact with your surface. Usually we interaction studies will do when we'll take one surface layer 2D material. Above that we'll keep some kind of like gas molecules or biomolecules or some kind of atoms or ions. Then we'll check how it will interact with that. In that case, what we need to do. So first you have to optimize your surface layer slab. Then you have to optimize that molecule separately. Then you have to keep your molecule above that surface. And for that, you have to create in three model. One model is for like top view model. Another one is like bridge view model. Another one is the halo site model. You have to keep it in the halo site. Then you have to optimize all the three structures. Then you have to find out that, so how the energy will changes. So which is more conform, which is more stable, which one is giving the best absorption energy. So that is more favorable. So we have to compare that, how it is changes in different view orientation. I hope it is clear to you, Ankita. Okay. So like that, from here you can find a lot of properties here. So here like atomic type, atomic number, their centers, distance matrix. Okay. Everything is there. You can scroll down and you can find it here. See here like different forces on each atoms. What is the forces along the XYZ coordinates? So here like R1, R2. So here they have like different optimized properties here. I can just, in this table, you can find out here. Okay. So like that, Akshay Kumar, you can find out from this file. All the properties you will get it here. The only thing is you have to properly read one by one where exactly it is. So I hope it is clear to you. If you have any questions, please write it in the chat box. If everything is clear, then type Y. Okay, so I can understand how much you got today's thing. Okay, I think there are no questions. So if there are no questions, I'm going to end the meeting. Okay. Okay, thank you so much for your time and your patience. So Chandra Prakash, sir, one request. Yeah, please tell. Saheb, thank you, sir. It is again a very informative session. Thank you, Saheb. So Chandra Prakash, sir, please tell, like you have told that you have one request. Please write it in here. I'm waiting for your what you are going to tell. So please, how to find the band structure and density of state from the Gaussian software. Sir, as I already told, it is quite difficult, but I can't show it here because if I want to show this band structure and density of state from the Gaussian software, I need to perform the calculation DOS and band structure. Okay. And it is take a lot of time. I can't show it in the live session, but I will tell at the end. I will tell you that I will show how to submit the calculation. Okay. No need to worry, I will show it. But I can't run the whole calculation. Okay. Just I will tell you like how to submit the calculation for like a density of state and band structure calculation. In that case, you can directly submit the calculation by using the Gaussian software. No need to use the Gauss view. Just prepare your input file and directly submit the calculation to the Gaussian software. Once your job is completed, you can just do the analysis by using the origin software or like your Excel software or some other like GNU platter. There are many things are there. I will do that. No need to worry. So, okay, Akshay, can you share your contact details? Yeah, definitely I will share. At the end of this workshop, I will share. Any other questions? So, Maruti Vani, today's class have some technical issues, sir. So, did not assign did simultaneously. So, please send today's class recordings, videos. Yeah, definitely I will share. Okay. So every day we'll get the recordings. No need to worry about that. So, any other questions? Okay, I think there are no questions. I will end the meeting. Thank you so much. Bye bye. Good night.